Welcome to The Sleepy Scientist. This channel is made for winding down at the end of the day, calm stories of sciences to help you relax and drift off to sleep. Tonight, we're exploring the quiet clouds that build the stars, the nebulae. These vast regions of gas and dust are where the universe recycles itself, turning starlight and shadow into new worlds. Before we begin, I'd love to know, where in the world are you watching from tonight? It's always interesting to see how far these calm explorations travel. If you enjoy these relaxing journeys through space, please give the video a like and subscribe to the channel. And to everyone who's already subscribed, thank you. Don't forget to tap the notification bell so you don't miss the next upload. Hopefully this video isn't too interesting, but if it does keep you awake, at least you'll learn something along the way. Now, let's begin. Have you ever wondered what's really inside those glowing clouds between the stars? The space between the stars isn't empty. It's filled with a quiet ocean of gas and dust, the raw material from which everything we see in the night sky is built. Astronomers call these regions nebulae, from the old Latin word for cloud. But unlike the clouds drifting over Earth, these cosmic mists can stretch for light years, glowing softly in colours shaped by chemistry and starlight. Some shine on their own, lit by newborn suns that flood them with ultraviolet light. Others reflect the glow of nearby stars, scattering it into pale blue fog. And some remain dark altogether, vast silhouettes that hide more light than they give away. Together they form the quiet architecture of the Milky Way, an invisible ecology of creation and decay. A nebula begins with atoms drifting in the deep cold, hydrogen, helium, and a trace of heavier elements. Gravity gathers them into loose threads. Time presses them closer. Within these delicate knots, temperature and pressure rise until something extraordinary happens, the first spark of fusion and the birth of a star. But nebulae aren't only cradles, they're also memorials. When stars like our Sun reach the ends of their long lives, they exhale their outer layers into space, forming glowing shells that drift outward for thousands of years. In other cases, massive stars end in explosions so powerful they shred themselves completely, seeding space with the ingredients for new worlds: oxygen, carbon, iron, and the quiet dust that will one day build planets and people. This cycle, birth, death, and renewal, is what keeps the galaxy alive, and tonight we'll drift through that cycle together, exploring how light, gravity, and time weave these luminous clouds into the story of everything. So take a deep breath and let's begin our journey through the nebulae, where the universe writes its poetry in mist. Out in the quiet reaches of space, enormous clouds drift between the stars. Astronomers call them nebulae. The word comes from Latin meaning cloud, though they're nothing like the clouds we see above Earth. They're much larger, much thinner, and far more patient. From far away they can look like soft smudges of colour, but up close they are grand structures of gas, dust and light that stretch across trillions of kilometres. Some are bright and glowing, some are dark and cold, and some are the final whispers of dying stars. At its simplest, a nebula is a region of gas and dust in space, but not all nebulae behave the same way. Astronomers sort them into families, each with its own personality. The first are emission nebulae, the showpieces of the cosmos. These are clouds that actually glow, lit up from within by the fierce radiation of young hot stars. The gas in these regions is mostly hydrogen, and when the ultraviolet light from those newborn stars strikes the gas, it strips away electrons and makes the atoms shine. The result is a deep red or pink glow, the fingerprint of hydrogen coming back together again. The Orion Nebula, glowing faintly in Orion's sword, is one of the brightest examples. Next come reflection nebulae, which don't glow on their own at all. They simply borrow the light of nearby stars, scattering it into view. The fine dust inside them reflects blue light more efficiently than red, just as our sky does, so they often appear as soft, silvery blue patches in the night. They are delicate, quiet, and easily lost in the brightness of other objects. Then there are the dark nebulae, the mysterious silhouettes of the galaxy. They don't shine or reflect, they block. These are the densest, dustiest parts of the interstellar medium, thick enough to hide the stars behind them. The famous Horsehead Nebula is one of these, its shape cut out of glowing red gas like a shadow against firelight. Inside these dark coarse clouds, where the light of the universe can barely reach, gravity begins to work in secret, gathering the first seeds of new stars. But not all nebulae are about birth. Some mark the final stages of stellar life. Planetary nebulae are the glowing shrouds left behind when stars like our Sun reach the end of their long, steady existence. As these stars run out of fuel, they shed their outer layers into space and their hot, exposed cores illuminate the gas around them. Despite the name, they have nothing to do with planets. The term dates back to the late 1700s, when early astronomers using small telescopes saw round, faint disks that reminded them of distant worlds. The name stuck, even though these objects are really the afterglow of stars, not the birthplaces of planets. Beyond those gentle shells are the most dramatic nebulae of all, supernova remnants. When a massive star runs out of nuclear fuel, it collapses and then explodes in a flash of unimaginable energy. The blast hurls the star's outer layers across space at thousands of kilometers per second, forming delicate webs and filaments that can stretch for dozens of light years. The Crab Nebula is one such remnant, the ghostly aftermath of a supernova that lit up Earth's sky in the year 1054. These remnants are cosmic recycling plants, scattering heavy elements like iron, calcium and gold into the galaxy, the raw materials for future stars, planets and life. Though they look thick and smoky in photographs, most nebulae are astonishingly thin. If you could scoop up a handful of nebula material, you'd find that it's emptier than the best vacuum humans can make in a laboratory. In many places, a cubic centimetre, about the size of a sugar cube, might contain only a few hundred atoms. On Earth, that would be called nothing at all, and yet stretched across dozens or hundreds of light years, that nothing becomes something magnificent. The sheer scale turns ghostly wisps into glowing tapestries of gas. It's more a cosmic perfume than a fog machine, faint, elusive, but unforgettable when gathered in great enough quantity. Most nebulae are made mainly of hydrogen, the simplest and most abundant element in the universe. Helium comes next, along with trace amounts of oxygen, carbon, nitrogen, and other heavier elements forged in stars. Dust, tiny solid grains of silicates and carbon compounds, makes up only a small fraction of the total mass, but it's crucial. Without dust, there would be no planets, no complex chemistry, and probably no life. These microscopic particles absorb and scatter light, helping to cool gas clouds and shape the flow of star formation. Seen through different kinds of telescopes, the same nebula can tell entirely different stories. In visible light, glowing hydrogen dominates. In infrared, telescopes peer through the dust to reveal the warm cocoons of hidden stars. In radio, astronomers can trace the cold molecular gas that marks the next generation of stellar nurseries. Nebulae are like multi-layered paintings, one colour showing birth, another decay, another the faint promise of worlds not yet formed. It's easy to forget, looking at the photographs from space telescopes, that those brilliant swirls of colour are made of physics, light interacting with atoms, dust and motion. But it's that combination of art and science that makes nebulae so captivating. They're not static, they're alive with change. Atoms drift, collide and glow. Gravity pulls, radiation sculpts. Over millions of years, shapes stretch and fade, creating vast mosaics that will one day disperse into the next generation of stars. So when astronomers talk about nebulae, they're really describing the raw pulse of the galaxy itself. Clouds that are born from stars, give rise to new ones, and scatter the elements that make everything from oceans to oxygen. These are not just clouds in space, they are the quiet architects of creation. And though they may seem distant and unreachable, every breath of air, every atom in your body once passed through one of them. The universe has been making and remaking itself through these clouds for billions of years, painting the night sky with the slow rhythm of light and time. Every glowing nebula in the night sky is a conversation between light and matter, a slow, radiant dialogue spoken in colours. The universe may seem dark, but it is full of quiet exchanges, atoms catching starlight, releasing it again, and in doing so painting the invisible air of space. To understand why these clouds glow, we have to follow the path of a single photon, a tiny particle of light, as it leaves a newborn star and meets the gas around it. When a star is young, hot and enormous, what astronomers call an O-type or B-type star, it burns with an intensity that would make our sun look pale by comparison. These stars shine mostly in ultraviolet light, invisible to the human eye, but powerful enough to shake electrons free from hydrogen atoms in the surrounding gas. This process is called ionization. It leaves behind clouds filled with charged protons and stray electrons bathed in the fierce radiation of the stars that created them. But space, even when electrified, doesn't stay chaotic for long. The freed electrons eventually find their way back to the protons, recombining to form neutral hydrogen once more. When they do, the atoms release energy as light, tiny bursts of colour, each one corresponding to a specific transition inside the atom. The most famous of these colours is the deep ruby red of hydrogen alpha light, which astronomers see at a wavelength of 656 nanometers. This glow is what gives emission nebula their warm reddish tones, the same crimson blush that threads through the Orion Nebula and the Lagoon. It's a process both violent and beautiful. Starlight strips the atoms bare, and then the atoms, in their slow return to calm, release light that fills the darkness around them. The result is a glowing cloud that seems to breathe, bright where stars are young and fading at the edges, where their influence wanes. Not all nebulae glow by their own power. Some shine with borrowed light. These are the reflection nebulae, calm blue-tinged clouds that shimmer by scattering the light of nearby stars. The principle is the same reason our sky looks blue. Shorter wavelengths of light are scattered more effectively by tiny particles. This is known as Rayleigh scattering. In the thin dust of a reflection nebula, like the one surrounding the star cluster in the Pleiades, this scattering turns the starlight into a soft azure haze. The larger dust grains inside the nebula add a touch of mere scattering, which spreads the light more evenly, giving the nebula its characteristic pale glow. The contrast between emission and reflection nebulae is striking. One is a forge, glowing from within as atoms are energized by starlight. The other is a mirror, quiet and passive, reflecting the light that reaches it, and yet both are linked by the same physics, the way tiny particles interact with waves of energy. To an astronomer, every colour in a nebula carries a story. Red tells of hydrogen's warmth. Green can come from doubly ionized oxygen, known as O3, glowing at 500 nanometers. Yellow or orange may come from sulfur, labelled S2. These particular emissions are sometimes called forbidden lines, not because they break any cosmic rule, but because they don't occur easily under Earth's dense conditions. In laboratories or in our atmosphere, the atoms collide too often for these fragile states to survive. But in the thin, almost silent vacuum of a nebula, an atom can linger long enough in an excited state to release this rare light. is the universe's version of a neon sign humming softly in colours we can barely imagine. Through the narrow eyes of a spectrograph, these lines become a pattern of brightness and darkness, a barcode of the cosmos. Each spike of colour corresponds to a specific element, letting scientists decode a nebula's composition and temperature. In this way, astronomers don't just see nebulae, they listen to them, like hearing a chord played on the strings of light. Hydrogen sings in red, oxygen hums in green, sulfur in deep orange. Together they create a spectral symphony that reveals not just beauty, but chemistry, age, and history. Modern telescopes use filters that isolate these individual notes. By capturing hydrogen alpha light, astronomers can emphasize the glowing regions of active star formation. With oxygen or sulfur filters, they can bring out the subtle contrasts that reveal the shapes of shock waves and cavities carved by stellar winds. Combined, these filtered views create the colourful composite images that fill astronomy books, though the colours are often assigned by choice, translated from invisible wavelengths into something our eyes can appreciate. The famous hues of red, green and blue seen in images from space telescopes aren't purely artistic, they're coded maps of the physics behind the glow. What might look like an abstract painting is in fact a scientific portrait. The wisps of green might mark regions of energized oxygen, while red traces clouds dense with hydrogen. The blue fringes show where dust reflects starlight or where ultraviolet light scatters through thinner regions of gas. Each colour layer adds another brushstroke to the story. You could think of the process like watercolour painting on a cosmic scale. The paper is the void of space, the pigment is the dust and gas, and the water is light itself, spreading and blending across invisible currents. Sometimes the strokes are sharp, carved by shock waves and stellar winds. Sometimes they fade gently like diluted colour bleeding into paper. Over time, gravity and radiation reshape the artwork, creating new forms while erasing the old. Even the most delicate nebula is a balance between energy and stillness. When the light from young stars fades, or when the dust grows thick enough to block it, the glow slowly dies out and the nebula returns to darkness. The atoms cool, the scattering stops, and the gas drifts quietly until another burst of starlight reignites it. In the vast rhythm of the galaxy, illumination is temporary, but never truly gone. Every time light meets matter in space, something is revealed. A photon that left a star millions of years ago might finally end its journey by striking a speck of dust, scattering towards an observer on Earth. That single encounter becomes part of the story we see through a telescope, one more thread in the luminous tapestry of the Milky Way. It's humbling to think that the faint colours of a nebula, stretched across light years of darkness, are all made from the simplest interactions. Electrons falling back into place, dust grains nudging light sideways, atoms whispering their energy into the void. Yet from that simplicity emerges some of the most breathtaking sights in the universe. When you next see a photograph of a nebula, glowing in impossible shades of red and blue, remember that those colours aren't just decoration, they are evidence. They are physics made visible. Every hue, every shimmer, every faint edge of brightness is the echo of a conversation between stars and the space around them. The mist of the universe, painted by light, is speaking quietly to anyone willing to look and listen. In the grand theatre of space, dust often plays the role of background scenery, quiet, overlooked and faintly mysterious. Yet without it, the universe would lose much of its depth, colour and texture. Dust is what sculpts starlight, giving form to the formless. It's the reason some nebulae glow softly and others vanish into shadow. It builds planets, shapes galaxies, and turns the simple act of starlight passing through space into a work of art. Cosmic dust isn't like the dust found on bookshelves or windowsills. It's made of microscopic grains, tiny solid particles that drift between the stars. Most are smaller than a wavelength of visible light, just a few tenths of a micron across. That's about the size of smoke particles or fine soot. Despite their size, they are made of sturdy stuff, silicates like olivine and pyroxene, bits of carbon, metallic iron, and even frozen mantles of water, methane, or ammonia. Each grain is a small but crucial ingredient in the chemistry of the cosmos. These grains are born in the atmospheres of old stars and in the explosive shells of dying ones. When a red giant swells near the end of its life, it gently blows away its outer layers, releasing carbon and silicon into space. Supernovae do the same, but with more enthusiasm, scattering their contents at thousands of kilometers per second. Over time, this debris mixes into the interstellar medium, where atoms condense around it like frost. The result is a fog of mineral and ice particles, thin beyond imagination, but spread over regions so vast that it changes how galaxies look. When starlight passes through a region filled with dust, it doesn't travel unscathed. Some of it is absorbed, some scattered, and some shifted in colour. The process is a bit like sunlight filtering through smoke or mist. The blue wavelengths, which are shorter, scatter more easily, while the redder light slips through. As a result, stars seen through dusty regions appear dimmer and redder than they truly are, a phenomenon called interstellar reddening. It's not that the stars themselves change colour, it's that the dust reshapes the light on its way to us. This simple trick of physics transforms our view of the galaxy. The bright bands of the Milky Way, seen from a dark countryside, are crossed by inky rifts and streaks. To the naked eye, they look like empty patches where no stars exist. But they're actually dense lanes of dust, blocking the light behind them. Through a telescope, these lanes reveal subtle, smoky textures, shadows with substance. They're places where light and matter wrestle in silence, where dust becomes both the canvas and the painter. The Horsehead Nebula is perhaps the most famous example. Against the glowing red curtain of the Orion region, a small dark shape juts upward, a profile of dust sculpted by light. It's not a solid structure, but a dense pocket of gas and particles that absorb almost all visible light, leaving behind only a silhouette. Its outline, resembling a horse's neck, is carved by ultraviolet radiation from nearby hot stars. Over time, this radiation slowly erodes the dust, peeling it away grain by grain, like wind shaping a desert dune. The Horsehead endures for now, but it's slowly being whittled down by the very light that reveals it. Farther away, in the constellation of Ophiuchus, the Snake Nebula twists through space, a dark filament curling through a pale star field. It looks almost alive, like smoke frozen in time. This is another masterpiece of dust, formed where turbulence, gravity and magnetic fields weave gas into long thread-like structures. Within those filaments, pockets of higher density may one day collapse into stars. The snake, then, is both sculpture and seed, a frozen snapshot of creation waiting to happen. What makes these forms so haunting is the way dust interacts with light. Each grain both hides and reveals. When light hits it, part of the energy is scattered away, redirected in random directions. Some of that scattered light reaches us, creating the faint halo seen around bright stars in reflection nebulae. The rest is absorbed, warming the grain slightly before it re-emits that energy as infrared radiation. To our eyes, the result is shadow. To an infrared telescope, those shadows glow faintly like embers in a cool fire. Dust is also magnetic in personality, if not in literal structure. Many grains align with galactic magnetic fields, their tiny shapes acting like compass needles. As starlight passes through, it becomes slightly polarized, meaning the light waves line up in a particular direction. By measuring that polarization, astronomers can map the invisible threads of magnetism that lace through the Milky Way. In this way, dust doesn't just block light, it carries secret information about the hidden forces that shape galaxies. Despite its reputation as an obscurer, dust is one of the most creative materials in the universe. It's the raw ingredient from which planets form. Inside dense clouds, grains begin to stick together, building larger clumps. Over time, those clumps grow into pebbles, then rocks, then worlds. Every solid surface, from the crust of Earth to the rings of Saturn, can trace its ancestry back to microscopic grains floating in some ancient nebula. What seems like nuisance and haze is actually the beginning of something tangible. Dust also shapes the colours of nebulae in subtle ways. In emission regions, dust absorbs some of the starlight and re-emits it in infrared, adding warmth to the glow. In reflection regions, the scattering by dust gives nebula their cool blues and silvers, and in dark nebulae, where light cannot penetrate, dust turns the cosmos into chiaroscuro, a play of shadow and radiance that artists on the whole Earth could only dream of. The balance between illumination and concealment gives the galaxy its character. Without dust, the Milky Way would look flat and sterile, a sky of uniform brightness with none of the mysterious depth we find so enchanting. Even the thinnest layer of dust can have dramatic effects. A cloud containing only a few atoms per cubic centimetre, almost pure emptiness, can dim starlight over hundreds of light years. Astronomers have to account for this when measuring distances, otherwise the universe would appear unfairly faded. It's as if someone had draped a sheer veil over the cosmos, subtle enough to overlook but strong enough to change everything we see, and yet, for all its influence, dust is fragile. Harsh ultraviolet radiation can destroy grains over time, and powerful shock waves from supernovae can shatter them into smaller pieces. But even destruction feeds the cycle. Fragments become the seeds for new grains, which grow again in the cooler parts of space. It's a slow, endless rhythm. Dust born from Voyager's stars, reshaping light and returning to the stars once more. To the human eye, a dark nebula might look like an absence, a hole punched into the stars, but in truth, it's a quiet presence, a whisper of structure in the vastness. Those faint silhouettes are reminders that even in the emptiest corners of the galaxy, there's architecture at work. Dust sculpts the light we see and hides the light we don't, turning the universe into a living gallery of shadows. So the next time you see an image of a nebula, a crimson glow, a blue mist, or a black cutout against the stars, remember that much of its beauty comes from the tiniest things imaginable. A single grain of dust can shape the way an entire region of the galaxy looks. The cosmos is not just painted by light, it is carved by the smallest of shadows. Among all the glowing clouds in the night sky, few are as familiar or as breathtaking as the Great Orion Complex, a vast region of gas, dust and newborn stars, stretching hundreds of light years across space. It's a whole neighbourhood of creation, a galactic workshop where the universe is still hard at work building suns and sculpting worlds. Even to the unaided eye, its presence can be felt. On a clear winter night, the three bright stars of Orion's belt point downward toward a faint, misty patch in the sword that hangs below. That gentle blur is the Orion Nebula, also known as M42, and it sits within one of the most active star-forming regions in the entire Milky Way. The Orion complex isn't a single object, but an entire family of nebulae, bound together. Dark clouds, bright emission regions, and expanding arcs of gas, all connected by the same thread of gravity and starlight. The grandest feature is Barnard's Loop, a vast crescent-shaped arc that stretches across Orion's entire constellation. It's so large that if your eyes could see its faint red glow, it would appear as a sweeping bow around the hunter's figure, spanning more than 20 full moons across the sky. This great loop is thought to be the ancient echo of a long-ago explosion, perhaps a supernova or a burst of stellar winds from massive stars that lived fast and died young. Its curved shape marks the outer edge of a giant bubble carved into the interstellar medium, and within that bubble lies the birthplace of countless new stars. Drifting inward from Barnard's Loop, the gas grows denser and brighter until we arrive at the beating heart of the complex, the Orion Nebula itself. Here, a giant molecular cloud collapses under its own gravity, forming clusters of hot, young stars that flood their surroundings with light and energy. The brightest of these lie in the Trapezium cluster, a tight group of 4 main stars that act like cosmic floodlights, illuminating the entire region. Though only a few million years old, mere infants by stellar standards, these stars are powerful enough to sculpt their environment. Their intense ultraviolet radiation heats and pushes away the surrounding gas, hollowing out a glowing cavity at the nebula's centre. It's an impressive sight, a cradle of stars that is also busy dismantling the very cloud that created them. The process is not gentle. The fierce stellar winds and ultraviolet radiation stream outward, evaporating nearby pillars of gas and shaping the nebula into ridges, arcs, and finger-like projections. It's easy to think of this as destruction, but it's also part of creation's rhythm. The same energy that disperses the old material triggers new collapses elsewhere, setting off the birth of more stars. In a way, the Orion Nebula is a self-sustaining workshop, the young tearing down walls so the next generation can rise behind them. You might call it a nursery where the infants are already throwing ultraviolet tantrums. Amid the chaos, smaller wonders hide in plain sight. Surrounding the Trapezium cluster are hundreds of tiny faint objects known as proplyds, short for protoplanetary disks. Each one is a small dusty cocoon orbiting a young star, potential solar system in the making. Some are little more than dark ovals silhouetted against the nebula light. Others shine as miniature crescents, their edges glowing where radiation from the cluster strikes them. These are the quiet hints of future worlds, places where dust will clump, form rocks, and one day perhaps build planets like our own. The sight of them feels like a glimpse of both the past and the future, how our solar system might once have looked, and how countless others are now beginning. The Orion Nebula is also remarkable because it's so close to us, only about 1,300 light-years away, practically next door in galactic terms. That proximity makes it one of the best-studied regions in astronomy. Every wavelength of light has been turned upon it, from X-rays to radio waves. In visible light, it glows with the deep red of hydrogen, the pale green of oxygen, and the faint blue of reflected starlight. In infrared, telescopes peer through the dust to reveal even younger stars hidden inside. Each layer of observation adds another piece to the puzzle, showing how complex and dynamic this stellar nursery really is. For all its scientific importance, the Orion Nebula also remains a favourite for casual stargazers. Unlike most nebulae, it's bright enough to see with the naked eye, appearing as a small fuzzy patch in Orion's sword. Through binoculars, it takes on the shape of a soft, luminous fan, a ghostly glow spreading out from a pinpoint of light. A small telescope reveals its structure, delicate veils of silver and green wrapped around a radiant core. It's one of those rare deep-ski objects that bridges the gap between imagination and observation. Even from the suburbs, with a bit of patience and clear air, you can see the same glowing nursery that ancient astronomers once wondered about. One of the most fascinating things about the Orion complex is how interconnected its pieces are. Barnard's Loop, the Orion Nebula, the nearby Horsehead Nebula, and the Flame Nebula. All these structures are part of a single vast molecular cloud complex, bound by shared origins and overlapping histories. The energy released by young stars in one part triggers the collapse of gas in another. Waves of motion ripple through the region, linking each pocket of creation to the next like the beats of a single heart. Even the colours we see are connected. The red from hydrogen emission, the blue from scattered starlight, and the black from dust lanes all speak the same language of transformation. For astronomers, Orion is a natural laboratory, a living demonstration of how stars and planets form. It's close enough to study in exquisite detail, yet large enough to represent the processes happening all across the Lagoon. In its glowing folds, we can trace every step of the stellar life cycle. Cold molecular gas collapsing into dense knots, the ignition of new suns, and the carving of cavities that prepare the way for the next wave of stars. It's as if the entire history of stellar evolution has been condensed into one patch of sky. But there's also something deeply human about Orion. For thousands of years, people have looked up at this constellation and seen a hunter, a god, a story in the stars. They couldn't have known that behind that familiar pattern lay a cradle of cosmic life, a place where the raw materials of existence are constantly renewed. The ancient myth spoke of Orion's strength, but the nebula that bears his name tells a softer truth, that creation and destruction are inseparable, that light is born from darkness, and that even in the coldest corners of space, new beginnings are always taking shape. So the next time you step outside on a clear winter night, look up at the hunter's belt and let your gaze fall downwards to that faint misty glow. In that small patch of sky, you are seeing a piece of the universe in motion. A cosmic nursery lit by stars only a few million years old. The light reaching your eyes left before the first cities were built on Earth, crossing more than 1,000 light years just to arrive now. It carries with it the story of creation, written in starlight and dust, waiting quietly above the rooftops for anyone willing to look up. In the vast tapestry of Orion's belt, two of the most striking scenes sit almost side by side: the Horsehead Nebula and the Flame Nebula. They are close neighbours in the sky, both nestled near the bright star Alnitak, the easternmost jewel of Orion's famous trio. Together they form a cosmic contrast, one dark and mysterious, the other bright and alive with light. Side by side they tell a quiet story about how dust and starlight shape the universe in opposite ways. The Horsehead Nebula, officially known as Barnard 33, is one of the most iconic silhouettes in all of astronomy. It isn't a solid object, but rather a dense column of cold gas and dust standing before a glowing red curtain called IC 434. The glowing background is made of hydrogen gas, illuminated by the ultraviolet light of a nearby massive star named Sigma Orionis. Against that soft radiance, the Horsehead's profile cuts a dark, distinctive figure, the shape of a rearing horse's neck, complete with a curved mane and muzzle. The resemblance is so uncanny that it feels sculpted, though of course it's just coincidence. This is nature's quiet gift to the human imagination, a masterpiece painted by physics, yet titled by pareidolia. The blackness of the Horsehead is not absence but density. The dust within it is thick enough to block nearly all visible light. Each grain absorbs or scatters photons, making the structure appear completely opaque. The gas is cold, only a few dozen degrees above absolute zero, and inside it, gravity is slowly pulling matter together into clumps that may one day ignite as stars. The outer layers, however, are under constant assault. Ultraviolet radiation from Sigma Orionis and other nearby stars strips away the edges, heating and evaporating the gas. The border where this erosion happens glows faintly, creating a thin halo along the Horsehead's crest. It's the line between darkness and dawn, the boundary where creation and destruction meet in silence. The Horsehead is surprisingly small in appearance, only a tiny blot in the sky, barely larger than the tip of your thumb at arm's length, but in reality it's vast. The head alone is several light-years tall, large enough to swallow our entire solar system many times over, yet it remains fragile, slowly thinning as radiation gnaws at its edges. In another few million years, the famous silhouette will be gone, dispersed into the wider Orion complex. But for now, it stands as one of the most beautiful examples of silhouette science, where light acts as a canvas and dust, invisible on its own, becomes the brush that paints upon it. Just a short distance away on the sky lies the Flame Nebula, catalogued as NGC 2024, glowing fiercely near Alnitak itself. At first glance, the two seem like opposites, one a dark figure cutting across light, the other a bright inferno burning through shadow. But both are shaped by the same forces, radiation, dust, and the delicate balance between energy and matter. The Flame Nebula gets its fiery appearance from a process called ionization. Ultraviolet light from Alnitak strikes the nearby hydrogen gas, exciting its atoms and causing them to emit a deep red glow. In the bright centre, the gas is so energized that even atoms of oxygen and nitrogen contribute their own greenish and bluish tones, giving the entire region a layered, flickering look, like embers in a quiet fire. The darker bands that seem to slice through the flame are not voids, but lanes of cooler dust silhouetted against the glowing gas behind them. These filaments wind through the nebula, sculpted by the magnetic fields and stellar winds that flow through the region. Astronomers studying the flame in infrared light have discovered clusters of young stars hidden within it, still wrapped in their birth cocoons. Invisible light there, invisible, veiled by the dense dust, but in infrared their warmth shines through. Newborn suns cradled in a glowing cradle. The flame's beauty comes from its contrast. In long exposure images, it looks like a candle burning quietly in the void, its base dark and heavy, its edges feathered with light. Yet the physics behind that beauty is simple and constant. The gas glows because electrons are falling back into place after being stripped away by starlight. The ridges and folds form because pressure and magnetic fields sculpt the flow of gas, creating ripples that we see as texture. And the soft flicker of brightness is not movement at all, just the gentle blending of countless glowing atoms spread across dozens of light years. Astronomers often refer to regions like this as ionization fronts. They are the visible boundaries between fully illuminated gas and the darker molecular material behind it. In the flame, these fronts trace the shape of the nebula like veins of light, glowing where ultraviolet energy meets the cool calm of unlit hydrogen. They show us that light does not simply illuminate the cosmos, it reshapes it. Each bright ridge marks a frontier where starlight has changed the chemistry and temperature of space itself. When we see the Horsehead and the Flame together, we are witnessing both sides of that frontier. One shows what happens when dust stands its ground, holding the light at bay. The other shows what happens when the light wins, pushing the darkness back. Between them, they tell a story of balance, creation and erosion, concealment and revelation, stillness and energy. From a poetic distance, the Horsehead looks like a single stroke of ink, and the Flame like a splash of colour beside it. Together they could be mistaken for deliberate artistry, as though the cosmos itself practiced calligraphy. In truth, they are the result of chance and time, pressure waves, radiation, and the invisible tug of gravity working together for millions of years. Yet their beauty feels intentional, and that feeling says something about us. Humans are pattern-seeking creatures, eager to find meaning and form in the clouds, even when the clouds are hundreds of light years away. When early astronomers first photographed the Horsehead at the end of the 19th century, they were captivated not by equations but by resemblance. It was as if the universe had briefly drawn something recognizable just to remind us we're part of its story. Even now, with powerful telescopes and digital detectors, the wonder remains. Modern images show details that early astronomers could never dream of. Wisps of gas curling around the Horsehead's mane, faint stars peeking through its edges, the flames delicate filaments etched like veins of smoke. Yet despite the high resolution, the feeling is still the same. These are sights that stir curiosity and calm in equal measure, proof that science and beauty often share the same light. For anyone with a small telescope, this region of Orion offers a glimpse of that quiet magic. The Flame Nebula can be seen from a dark site as a faint patch of light near Alnitak, its glow softened by the star's brilliance. The Horsehead is far subtler, visible only under perfect conditions and usually through special filters that isolate hydrogen's red light. But knowing they are there, vast clouds sculpted by starlight, adds depth to every glance at Orion's belt. Behind those bright, familiar stars lies a world of shadows and fire, of dust against the dawn. The Horsehead and the Flame remind us that the universe isn't just a place of explosions and extremes. It's also an artist of quiet contrasts. In one small corner of the sky, light and darkness meet, dance, and define each other. The glowing gas and the ink-black dust don't compete, they complete the picture. And in that balance we can see not only how stars are born, but how beauty itself can arise from physics, written gently in the language of light. There are few sights in the universe as instantly recognizable, or as quietly awe-inspiring, as the towering shapes of the Eagle Nebula, catalogued as M16. Rising like ancient stone monuments, these structures are known as the Pillars of Creation, a name that manages to be both poetic and accurate. They are colossal columns of gas and dust, each one several light-years tall, standing in the middle of a bright star-forming region. Within them, new stars are being born even as the surrounding light tries to tear them apart. At first glance, the scene seems serene. Great pillars floating in a golden haze, surrounded by newborn stars. But behind that calm appearance is a storm of energy. The Eagle Nebula is home to a cluster of massive young stars whose radiation is powerful enough to reshape the landscape around them. Their ultraviolet light ionizes the gas, stripping away electrons and causing the surrounding hydrogen to glow. The fierce stellar winds they produce push outward in all directions, sweeping up the surrounding material and hollowing out vast cavities in the cloud. The edges of those cavities are where the pillars stand, the last dense remnants of a cloud that is slowly being sculpted away by light. The physics is a delicate balance between resistance and surrender. Inside each pillar, the gas is dense and cool, protecting the embryonic stars that are forming within. The surrounding radiation, however, heats and evaporates the outer layers, creating a thin, glowing skin. This process is called photoevaporation, and it's the reason the pillars have such sharply defined edges. It's as if invisible winds are sanding them down, slowly thinning their outlines over thousands of years. The result is breathtaking. These immense towers are not solid at all, but fragile columns of mist, eroding one atom at a time. When high-energy radiation from the nearby stars strikes the tops of the pillars, it creates bright ridges and shock fronts, ripples of compressed gas that travel downward into the columns. These waves of pressure can sometimes trigger new rounds of star formation inside, squeezing the gas just enough for gravity to take over. It's a gentle chain of cause and effect, old stars giving birth to new ones through the very forces that will later destroy them. Creation and destruction, again, are two sides of the same cosmic coin. The Pillars of Creation became famous in 1995 when the Hubble Space Telescope captured their now iconic image. It showed 3 towering fingers of gas, tinted in shades of gold, blue and green, rising out of a glowing nebulous sea. That image became one of the most recognizable photographs in astronomy, a picture that managed to blend science and art so perfectly It hung on classroom walls and living room posters alike. It gave the public a rare glimpse of what star formation actually looks like, not as an abstract concept, but as something tangible and breathtaking. In more recent years, the James Webb Space Telescope turned its gaze on the same scene, revealing it in even greater depth. Where Hubble saw texture and colour, Webb saw structure and temperature. Its infrared eyes can pierce through the dust that blocks visible light, exposing stars that were hidden before. Tiny points of heat nestled within the columns, shining faintly through the fog. In the Webb images, the pillars look warmer, more translucent, and strangely alive, as though they are glowing from within. The two views together, Hubble's visible light masterpiece and Webb's infrared vision, are like two layers of the same painting, one showing the surface, the other revealing what lies beneath. What both telescopes reveal is the extraordinary complexity of feedback in star-forming regions. The massive stars at the heart of the Eagle Nebula are both creators and destroyers. Their light compresses some clouds into new stars while dispersing others entirely. The glowing cavity around the pillars is filled with gas heated to thousands of degrees, expanding outward like a slow-motion explosion. The edges of that cavity are the sculpted walls we see, the living boundary between what was and what is becoming. To our eyes, these processes are frozen in time, but in reality they unfold across vast timescales. A single pillar might persist for a few 100,000 years before being eroded completely. To the universe, that's a fleeting moment. Yet even in their brief existence, these structures manage to leave a legacy. The stars born within them will live for billions of years, long after the pillars themselves have vanished. It's a quiet lesson in cosmic patience. Everything in the universe is temporary, but even temporary things can create something lasting. Astronomers believe that the Eagle Nebula lies roughly 7,000 light-years away, near the constellation Serpens. The central cluster of young stars, known as NGC 6611, is only a few million years old. To put that in perspective, if the galaxy were a calendar year old, this region would have formed within the last few seconds before midnight. And yet, in those few cosmic seconds, it has already produced hundreds of new stars, each with the potential to form its own planetary system. The pillars themselves are only one part of a much larger complex, stretching across dozens of light-years. Beyond them are other sculpted shapes, arches, knots and globules, all created by the same interplay of radiation and gravity. Each shape marks a moment in the evolution of the cloud. Some are being born, others are fading, and a few have already collapsed into clusters of stars. Together, they form a landscape that is both familiar and alien, like clouds seen through a slow, dreamlike time-lapse. From an artistic perspective, the pillars of creation are irresistible. They look solid enough to climb, yet they are made of near nothing. Gas so thin that a cubic meter contains fewer particles than the best vacuum on Earth. And still that near-nothingness is capable of extraordinary things. Within its cold interior, tiny pockets of density collect into spheres, heating as they collapse until, one day, they ignite. The universe takes something invisible and makes it shine. If you could watch the Eagle Nebula over millions of years, it would appear to breathe. New stars would flicker on, sending waves of radiation through the cloud. The pillars would shrink, crumble, and finally dissolve, replaced by open clusters of brilliant young suns. The light that now reveals them would one day erase them entirely. But that's the nature of creation in space, beauty born from impermanence. The story of the pillars of creation isn't just about one nebula. It's about the balance of forces that govern all star formation. It's about how light, gravity and time interact to turn cold gas into brilliance. And it's about how fragile forms can shape eternity. The next time you see the famous image of those towering columns, remember that you're looking at a fleeting moment in a very long story, a single frame in a film that's been running for millions of years. The Eagle Nebula reminds us that even in the calmest corners of the sky, entire worlds are being made. Behind every glowing cloud is the quiet struggle between light and darkness, between creation and dissolution. And in the midst of that struggle, beauty emerges, soft, luminous, and patient beyond imagination. In the southern sky, beneath the bright sprawl of the Milky Way, lies one of the grandest and most chaotic star-forming regions ever observed, the Carina Nebula, catalogued as NGC 3372. It is a colossal storm of light and gas, a cosmic landscape so vast that it could swallow the entire Orion Nebula dozens of times over. If the night sky were a painting, Carina would be the wild, swirling section where the artist's brush caught fire. This nebula is not merely glowing, it is boiling. Inside its enormous volume, massive stars pour out radiation, wind, and heat on a scale almost impossible to imagine. These are some of the most energetic suns in our galaxy, each millions of times brighter than the sun and hundreds of times heavier. Their combined output sculpts the gas around them into ridges, cavities and towers that twist and churn like clouds in a slow-motion storm. The result is a region alive with motion, turbulent, luminous, and breathtakingly beautiful. At the heart of this cosmic tempest lies one of the most dramatic stars in the universe, Eta Carinae. It's a name whispered with both awe and caution in astronomical circles, a reminder of how powerful and unpredictable stars can be. In the mid-19th century, Eta Carinae underwent what's known as the Great Eruption. For a few shining decades, it became the second brightest star in the entire night sky, outshone only by Sirius. But it wasn't a true supernova. Not quite. Instead, it expelled several solar masses of gas and dust into space, creating a pair of glowing lobes that now form the Homunculus Nebula, a tiny hourglass-shaped cloud nestled within the larger Carina complex. That eruption reshaped the surrounding region, adding turbulence and structure to an already restless nebula. The expanding shells from Eta Carinae collided with nearby gas, compressing it and setting off the new waves of star formation. In that sense, the event was both violent and creative, a stellar tantrum that left behind new generations of stars. Even today, Eta Carinae continues to shine as an unstable beacon, teetering on the edge of collapse, its fate uncertain. One day, it will almost certainly end in a supernova, an explosion that will briefly outshine the entire galaxy before fading into memory. But the Carina Nebula is far more than the story of one star. It's an ecosystem of energy, shaped by thousands of suns at different stages of life. The radiation pouring out from these stars creates enormous bipolar flows, jets and outbursts that sweep through the nebula, colliding and merging like ocean currents. Where these flows meet, shock fronts form, lighting up the gas in intricate filaments. The ridges and arcs that result look almost sculpted, each one marking a place where pressure, gravity and magnetism reached a temporary truce. If we could see the Carina Nebula in motion, it would resemble weather, but not the kind we know on Earth. There are no winds in the human sense, only the push of radiation and plasma moving through the interstellar medium. Yet the result is eerily similar. Clouds twisting into spirals, fronts of energy sweeping through space, calm pockets forming in the eye of the storm. Astronomers sometimes describe it as turbulent feedback, but the phrase hardly captures the grandeur of it, the way entire regions of gas ripple and shimmer under the breath of nearby stars. The Carina Nebula's beauty lies in its contradictions. It is both luminous and shadowed, violent yet graceful. The same energy that creates its breathtaking glow also threatens to unmake it. The ultraviolet radiation from the most massive stars, particularly the O-type giants, ionizes the surrounding hydrogen, creating great glowing walls of red and pink. At the same time, those same photons erode the very clouds that feed star formation, chipping away at the nebula's edges and sending tendrils of gas streaming outward into space. Creation and destruction exist side by side here, entwined so closely they can't be separated. Running through this vast chaos are magnetic fields, invisible but vital. They act like unseen threads, shaping how gas and dust move. Where the magnetic lines twist, the gas follows, creating long, braided filaments that stretch for light years. These structures are not random. They are the fingerprints of order within turbulence, the subtle choreography of forces working in balance. Without magnetism, the Carina Nebula would be a shapeless fog. With it, we see structure, patterns that hint at a kind of cosmic design. One of the most fascinating aspects of Carina is the scale of its energy budget. The combined luminosity of its central stars produces enough radiation to ionize gas over hundreds of light years. The stellar winds alone, streams of charged particles moving at thousands of kilometers per second, exert enormous pressure, capable of clearing entire cavities of gas. These winds sweep up material into shells and bubbles, compressing it at the edges where new stars can form. The process repeats endlessly, creating layers of birth and decay stacked upon each other like geological strata. To human eyes, the Carina Nebula appears as a rich swirl of golds and reds when captured through space telescopes. The colours come from different elements glowing in response to the flood of radiation: hydrogen in crimson, oxygen in teal, sulphur in orange. Between these glowing curtains lie darker pockets of dust, where gravity still holds sway and light can't yet penetrate. These are the quiet corners of the storm, the wombs of future stars. The contrast is breathtaking. Brilliance beside shadow, chaos beside calm. It's tempting to think of Carina as a kind of celestial symphony, an orchestra conducted by radiation and time. Each instrument plays its part, stars pulsing in light, gas clouds humming in emission lines, shock waves drumming across the void. Yet even in its loudest moments, the overall impression is one of balance. The violence is softened by scale, stretched out over millions of years. To us, frozen in a single instant of that great time span, it feels peaceful, almost meditative. The Carina Nebula also offers a glimpse of what our own region of space might once have looked like. Billions of years ago, the Sun was born in a similar cloud, surrounded by sibling stars and bathed in ultraviolet light. The processes shaping Carina today, the compression of gas, the carving of cavities, the gentle collapse of dense cores, are the same processes that once built the solar system. Looking into Carina's glowing depths is, in a way, looking back into our own beginnings. Astronomers have often described Carina as Orion on steroids, but that phrase undersells its grandeur. The entire region is alive with extremes, from the tiny knots of star formation buried deep within its ridges to the colossal arcs that stretch across hundreds of light years. It's not just a nebula, it's a galactic weather system, driven by the push and pull of energy on a scale that dwarfs imagination. And yet, despite all that power, the view remains calming. The nebula's luminous waves and soft folds evoke the same stillness that ocean waves do when seen from far above. Even its explosions seem to happen in slow motion, stretched across epochs too vast for urgency. It's the universe's way of reminding us that creation doesn't have to be hurried, and that even storms can be beautiful when watched from the right distance. One day the Carina Nebula will fade. Its gas will disperse, its massive stars will explode, and its light will dim. But for now, it stands as a living portrait of cosmic weather. Bright ridges flickering like lightning frozen in time, magnetic currents swirling like invisible wind, and the faint promise of new stars forming quietly within. It is a storm that sings softly, a tempest wrapped in serenity, proof that even the most violent forces in the universe can move with grace. In the direction of the constellation Sagittarius, where the Milky Way arches brightest across the summer sky, two of the most enchanting nebulae sit side by side, the Lagoon Nebula, also known as M8, and the Trifid Nebula, known as M20. They share the same stellar neighbourhood and even seem to overlap from our viewpoint, but they are distinct in character, two clouds painted on the same canvas, each glowing in its own style. Together they create one of the most photogenic regions in the sky, a scene of glowing reds, soft blues, and shadowy blacks, gently woven together like an interstellar watercolour. The Lagoon Nebula is the larger of the two, sprawling across a region more than 100 light-years wide and glowing with the unmistakable crimson hue of hydrogen. It's what astronomers call an H2 region, a cloud of ionized gas where new stars are forming, and young massive suns light up their surroundings. The central area of the lagoon is home to a cluster of hot, energetic stars known as NGC 6530. Their radiation floods the surrounding hydrogen with ultraviolet light, stripping electrons from atoms and causing them to emit that deep red glow we associate with star-forming regions. When viewed through a telescope, the lagoon looks like a pool of soft light, rippling and uneven, its edges fringed with darker lanes of dust. That appearance is what inspired its name. In long-exposure images, it reveals complex folds and filaments, like waves captured mid-motion. Near the centre lies a bright knot of gas called the Hourglass Nebula, not to be confused with the more famous Planetary Nebula of the same nickname, where young stars are emerging from cocoons of dust. The light they produce illuminates the gas from within, making it appear almost molten, as though a quiet fire burns behind the cloud's surface. The lagoon is a dynamic place, constantly shaped by the feedback of its own children. Stellar winds from newly formed stars push outward, carving cavities and compressing gas in surrounding regions. Those compressed pockets can collapse into new stars, continuing the cycle of birth and renewal. It's a reminder that in space, creation often happens through disturbance. Peace comes after turbulence, not before it. The lagoon's tranquil glow hides a restless process, one that has been unfolding for millions of years and will continue long after its current stars fade. Just above the lagoon lies the Trifid Nebula, smaller but every bit as captivating. Its name means divided into three, a nod to the striking dark lanes that slice through its circular form like flower petals. These dark streaks are not empty gaps, but dense ribbons of dust that block the light behind them. They divide the nebula into three bright lobes, sometimes four depending on how you look at it, creating one of the most elegant examples of contrast in the sky. The Trifid seems designed for the eye, structured, symmetrical and perfectly balanced between light and shadow. But what makes the Trifid truly fascinating is its diversity. It isn't just one kind of nebula, it's three at once: emission, reflection and dark. The inner regions glow in the same reddish hydrogen light as the lagoon, marking the areas where young stars are energizing the gas around them. Surrounding that is a halo of pale blue light, the signature of reflection, where dust scatters the starlight from nearby sources rather than generating its own. And cutting through it all are those dark dust lanes, the same kind that form the silhouettes in nebulae like the Horsehead. In one compact region, the Trifid shows all three personalities of interstellar clouds, glowing, reflecting and concealing. At its centre is a newborn cluster of stars dominated by a single massive one whose energy shapes the whole region. The ultraviolet radiation from this star ionizes the inner gas, while also pushing back on the dust farther out, creating a layered appearance that looks almost three-dimensional. Through a telescope, the Trifid's core seems to shimmer, as though light were being filtered through stained glass. The red emission and blue reflection overlap subtly, producing a lilac hue in some places, the cosmic equivalent of colours blending on a painter's palette. While the lagoon feels grand and expansive, the Trifid feels intimate, almost delicate. Together they form a perfect visual duet. The lagoon's wide red glow provides the warmth, while the Trifid's cool blues and intricate shadows add contrast and texture. The two nebulae are actually separated by several thousand light years, but from Earth they appear close enough to fit in the same wide-field view. It's a fortunate alignment, one that allows us to see in a single glance nearly every way that light and dust can interact in space. This meeting of hues, warm red, cool blue and velvet black, is more than an aesthetic coincidence. It's the product of the physics that governs the interstellar medium. Hydrogen, the universe's simplest element, produces the red. Dust particles acting as cosmic mirrors scatter the blue, and the densest clumps of gas absorb everything, leaving black. Each colour is the visual echo of an atomic process, and together they form one of nature's most elegant compositions. The Lagoon and Trifid nebulae are also wonderful reminders that the night sky isn't static. These regions evolve over time, just at a pace too slow for us to witness directly. In a few million years, the massive stars in the lagoon will explode as supernovae, sending shock waves through the surrounding gas. Those blasts will compress and heat the Trifid's outskirts, perhaps sparking new rounds of star formation. Eventually, both clouds will thin and disperse, leaving behind clusters of bright young stars that drift apart through the galaxy. What we see tonight is only a single frame in that long story. The moment when light, dust and gravity are perfectly balanced. For observers on Earth, the two nebulae are accessible treasures. The lagoon is visible even through binoculars under dark skies, a faint glowing patch nestled in the Milky Way's crowded heart. The Trifid is fainter, but with a small telescope its trilobed pattern becomes clear, the dust lanes cutting elegantly through the glow. To know that each patch of light represents a region hundreds of trillions of kilometres across is both humbling and comforting. The sky above us may seem distant, but it's filled with the same physics that shapes everything around us, the same elements that make up our air, our water and our bodies. In the Lagoon and Trifid nebulae, we see the universe's palette at work, clouds painted not with pigments, but with energy and time. They remind us that beauty in space is not an accident, but a consequence of laws playing out on grand scales. Where dust and light meet, colour blooms. Where darkness intrudes, shape is born. It's a gentle lesson written in starlight, that contrast creates meaning, and that even in the endless expanse of the cosmos, balance can still be found. Some nebulae seem to prefer order over chaos, great geometric shapes carved into the fabric of space. Among them are two that feel like opposites made to share a page: the Rosette Nebula, a near-perfect cosmic ring, and the California Nebula, a long glowing ribbon stretched like light itself. One is circular and blooming, the other narrow and flowing. If the galaxy were a bakery, they'd be a cosmic donut and a very long baguette, both baked in starlight. The Rosette Nebula, catalogued as NGC 2237 through 2239, lies about 5,000 light-years away in the constellation Monoceros, the Unicorn. It's a spectacular flower of hydrogen gas roughly 100 light-years wide, glowing in deep red and pink hues. At its centre sits a young star cluster known as NGC 2244, whose bright hot stars provide the energy that lights up the surrounding petals. These massive stars are only a few million years old, but their fierce radiation and stellar winds have already reshaped their birthplace. As the cluster formed, it began to clear the gas and dust from its centre, The combined effect of the star's ultraviolet light and the outflow of particles from their surfaces pushed the surrounding material outward, carving an enormous hollow in the middle of the cloud. The glowing ring that remains, the rosette, is what astronomers call an H2 region, a shell of ionized hydrogen gas lit by the very stars that created it. The symmetry is so striking that it's easy to imagine it as intentional, though it's purely the result of physics, light and motion finding balance in 3 dimensions. Inside the ring, the gas density is much lower, leaving a clear view into the central cluster. The stars there continue to influence the shape of the nebula, their radiation driving a slow wind outward in all directions. Over time, that flow creates a phenomenon known as a champagne flow. It's an apt name. Imagine the nebula as a bottle of bubbly, its interior filled with hot ionized gas under gentle pressure. When that gas finds an opening, a region where the density drops, or a cavity connects to the wider interstellar medium, it flows outward in a smooth, expanding stream, like champagne escaping from the neck of a bottle. This process helps to disperse the nebula over time, gradually blending it into the surrounding space. The Rosette Nebula, then, is a snapshot of a transitional stage, a cloud halfway between dense molecular chaos and the clear calm of open space. Eventually, its gas will fade and its stars will drift apart, leaving behind only the faintest trace of what once was a brilliant bloom. But for now, it remains one of the most beautiful examples of feedback in action, stars shaping the very clouds that gave them life. The rosette is also a reminder that the forces driving star formation aren't explosive in the usual sense. They are steady, persistent, and graceful. The radiation pressure from a star cluster can take millions of years to push the surrounding gas into a shell, but when it does, the result is remarkably uniform. Astronomers studying the rosette often describe it as a laboratory of equilibrium, where the push of light and the pull of gravity find a temporary truce. Its edges glow with hydrogen alpha light, tracing the delicate boundary between the ionized interior and the colder molecular gas outside. And then there's its quieter neighbour on the cosmic stage, the California Nebula, or NGC 1499, found in the constellation Perseus. This nebula earns its name from its unmistakable shape. When photographed, it resembles the outline of the state of California. Unlike the rosette, which glows from the combined energy of many stars, the California Nebula owes its light almost entirely to one, the bright blue-white supergiant G Persei, also known as Menkib. G Persei is a hot O-type star radiating intense ultraviolet light that ionizes the hydrogen in the surrounding cloud. The result is a long, gently glowing filament of gas nearly 100 light-years in length. The nebula's reddish colour comes from hydrogen alpha emission, while subtle hints of blue and violet trace areas where the light from G Persei scatters off dust grains. It's a perfect example of how a single star can act as both artist and architect, shaping a vast region of space all on its own. Unlike the rosette's symmetrical ring, the California Nebula is elongated and diffuse, with soft gradients and faint textures that fade seamlessly into the darkness around it. It's not as sharply defined, but that's part of its charm. Where the rosette is a dramatic display of structure, the California is gentle, a slow exhalation of light that stretches across space like a beam caught in fog. In its calm simplicity, it shows how small differences in geometry and environment can lead to completely different cosmic personalities. The California Nebula also offers a glimpse into the chemistry of space. Within its gas, ultraviolet light from G Persei drives photochemical reactions, breaking apart molecules and creating new compounds. This process alters the balance of carbon and oxygen species in the region, shaping how dust grains form and evolve. It's a quiet kind of alchemy, happening not in furnaces or laboratories, but in the cold between the stars. Both the Rosette and California Nebulae reveal how feedback, the influence of stars on their birth clouds, governs the evolution of galaxies. In the Rosette, feedback takes the form of expansion, a collective wind from many stars carving a bubble of light. In the California Nebula, feedback is more subtle, a single star's radiation gently energizing a linear stream of gas. Together they illustrate the range of the cosmos's creative tools, from collective effort to solitary brilliance. Visually, the two are complementary. The Rosette's circular symmetry feels almost architectural, while the California Nebula's elongated shape feels natural and free-flowing. One draws the eye inward, the other outward. If the Rosette is a closed system, a self-contained bloom, the California is an open road stretching endlessly along the galactic plane. It's the difference between a cathedral and a river, both awe-inspiring but in very different ways. For observers, both nebulae are rewarding targets. The Rosette can be glimpsed even through binoculars under dark skies, appearing as a faint patch with a star cluster in the middle. Through a telescope with a hydrogen alpha filter, the circular glow and faint filigree become visible, like frost forming on glass. The California Nebula, by contrast, is best appreciated in wide-field photographs. Its faint light spread too broadly to be captured in small instruments. Long exposures reveal its delicate texture and smooth gradients, the subtle interplay between light and shadow across its 100 light-year expanse. What makes these two nebulae especially poetic is the way they demonstrate the quiet persistence of light. Neither is a violent explosion or a dramatic outburst. Both are sustained glows, the product of steady radiation working over unimaginable timescales. The Rosette's expanding bubble and the California's flowing beam are part of the same continuum of creation, showing how stars continually reshape their environments, sometimes loudly, sometimes softly. And so, across thousands of light years, the cosmic donut and the very long baguette continue their slow dance. One curves inward, embracing its stars in a glowing ring. The other stretches outward, following the pull of a single beacon. They are both reminders that the universe, for all its complexity, often works in simple patterns: pressure, radiation, motion, repeated endlessly in different forms. From the elegant ring of the Rosette to the gentle beam of the California Nebula, space reveals its artistry not through haste or noise, but through patience. It takes its time to bake its masterpieces, one glowing shape at a time. Not all beauty in the cosmos comes from light. Some of it lives in shadow, in the places where starlight is silenced by dust, and the sky seems to fold inward on itself. These are the dark nebulae, the quiet counterpoints to the bright clouds that fill astronomy books. At first glance, they look like empty patches, as though someone had smudged out the stars with a thumbprint. But the darkness isn't absence. It's the opposite. It's the presence of matter, thick, cold, and full of potential. A dark nebula is a cloud of gas and dust so dense that it blocks the light of the stars behind it. If a glowing nebula is a lantern, a dark one is the lampshade, revealing shape through what it hides. The dust grains inside these clouds are efficient absorbers of visible light, particularly blue and ultraviolet wavelengths. That's why the stars behind them appear dimmer and redder, and why the darkest regions seem utterly black. They aren't holes in the sky, they're silhouettes, marking where the universe is quietly storing its raw materials for future stars. The best known of these silhouettes in the southern hemisphere is the Coalsack Nebula, a dark patch near the bright pattern of the Southern Cross. To the unaided eye, it's striking, a gaping void cutting into the Milky Way's glowing band. For centuries, it's been part of the night sky's mythology. To indigenous peoples of Australia, the Coalsack isn't emptiness but a shape, the head of the emu in the sky, a great celestial bird whose body is formed by other dark clouds trailing along the Milky Way. In their stories, the emu's seasonal position in the sky marks times for hunting and gathering, making the Coalsack not just a visual landmark, but a calendar written in shadow. Early European astronomers, seeing the same feature, described it simply as a black nebula, a curious term that captures the contradiction perfectly. How could something invisible still be something? But with better telescopes and infrared detectors, astronomers came to understand that the Coalsack is far from empty. It's a cold molecular cloud roughly 600 light-years away, stretching across about 70 light-years of space. Inside, the temperature hovers just a few degrees above absolute zero, and the density is high enough for molecules like carbon monoxide and ammonia to form. These are the first steps towards star formation, the earliest whisper of light to be. The Coalsack's edges glow faintly in infrared images, where hidden stars warm the dust just enough to make it shine. Deeper inside, however, everything is dark and still. The gas is shielded from external radiation, allowing gravity to work undisturbed. Over millions of years, small pockets within the cloud will collapse under their own weight, forming dense cores. Within those cores, temperature and pressure rise until nuclear fusion ignites, the first flicker of a new star. From afar, that process looks like creation from nothing, but in truth it's creation from darkness. The Snake Nebula, catalogued as Barnard 72, offers another view of this quiet art. It's smaller and more intricate than the Coalsack, a sinuous filament of dust twisting through the constellation Ophiuchus. Seen through a telescope, it looks exactly as its name suggests, a black serpent coiling across a field of stars. The contrast is sharp, as if someone had drawn it with ink. But once again, that darkness is not a void. It's a dense, cold strand of gas and dust, part of a larger complex of molecular clouds. In the snake, the dust is arranged in a thin filament, perhaps sculpted by magnetic fields and turbulence. These filaments are the arteries of star formation, narrow channels that feed material into denser knots where stars will eventually emerge. The entire structure is delicate, just a few light-years wide but long enough to thread across the sky. Infrared observations reveal young protostars embedded within it, invisible in visible light but glowing faintly in the far infrared. They are the eyes of the serpent, faint, embryonic stars quietly stirring inside their dusty cocoons. What makes dark nebulae like the snake so intriguing is how much they hide. In visible light, they are opaque. In radio and infrared wavelengths, they come alive. Radio telescopes can detect the faint emissions from molecules such as carbon monoxide, tracing the cold gas flows inside. Infrared telescopes like Spitzer and the James Webb reveal the faint warmth of dust grains, mapping out the internal structure. From these observations, astronomers can reconstruct the architecture of these clouds, their filaments, knots and cores, learning how turbulence, gravity and magnetic fields work together to build stars. Inside these molecular clouds, conditions are extreme but gentle. Frigid temperatures, low pressures, and slow motion. A typical particle drifts only a few hundred meters per second, walking pace on a cosmic scale. Collisions between atoms are rare, and yet over vast timescales they add up. Molecules form on the surfaces of dust grains, grow more complex, and eventually become the ingredients for the chemistry itself. These are the same kinds of clouds that billions of years ago gave birth to the sun and the planets. In every dark nebula, the story of our own origins is quietly rehearsing itself again. The Coalsack and the Snake show that the universe doesn't always announce its creativity with fireworks. Sometimes it works behind curtains. The bright nebulae, the Orions, the Carinas, the Lagoons, are the showpieces, the finished works on display. The dark ones are the studios, where the next masterpieces are being prepared. What we see as shadow is actually the scaffolding of the future, the foundation upon which light will later shine. There is also a peculiar beauty in how these clouds interact with their surroundings. Their edges often glow faintly from reflected starlight, or from the gentle ionization caused by nearby stars. In some cases, tendrils of dust appear to curl away from the main body, shaped by passing shock waves or magnetic tension. The interplay of these forces turns the clouds into evolving sculptures, their forms changing slowly but constantly over millions of years. One day, a dark patch like the Snake will vanish completely, dispersed into the surrounding space as its gas is converted into new stars and planets. But until then, it will continue to drift, a silhouette against infinity. When you look at a photograph of a dark nebula, the mind naturally wants to fill in the blank, to imagine something hiding inside the shadow. In a way, that instinct is correct. There is something there, though it moves too slowly and glows too faintly for us to see directly. The darkness isn't a barrier, it's an invitation. It reminds us that the universe doesn't need to shine to be alive. Sometimes the most profound processes take place in cyanas, in regions that appear empty, but are rich beyond measure. From the Coalsack's vast quiet curtain to the Snake's delicate meandering form, dark nebulae are the negative space of the galaxy's art, the parts that make the light meaningful. Without shadow, brightness loses context. Without absence, presence means nothing. In the dark clouds of the Milky Way, the universe practices patience. It gathers, it cools, it waits. And when the waiting is over, the darkness itself will give birth to the next generation of stars. Proof that even in the most silent corners of the sky, creation never truly sleeps. Every star begins as a whisper in the dark, a faint ripple inside a cold cloud of gas and dust. From the outside, nothing seems to be happening. The cloud drifts silently through space, dim and unremarkable. But within, gravity is beginning its slow, patient work. Over millions of years, that invisible pull gathers atoms together until density builds, pressure rises, and the first signs of a star begin to take shape. The process is calm when described, yet it's one of the most profound transformations in the universe. The birth of light from darkness. It all starts with fragmentation. Molecular clouds, those swirling nebulae filled with hydrogen, helium and dust, are not uniform. Slight differences in density, temperature or magnetic fields cause parts of the cloud to clump together more tightly than others. Over time, these tiny irregularities grow. Denser regions pull in more material, becoming even denser, while the surrounding gas drifts toward them. The once smooth cloud begins to break into smaller and smaller pieces, each one the seed of a future star. These fragments, often only a few light years apart, form the skeleton of what will eventually become a star cluster. Within each fragment, gravity continues to work. The gas contracts, heating up as particles collide more frequently. The result is a dense core, a cold but compact knot of material just a few thousandths of a light year wide. Temperatures inside these cores are still frigid, typically around 10 to 20 degrees above absolute zero, but they are much warmer than the space around them. As they contract, they become opaque to radiation, trapping heat and slowing the collapse slightly. It's like a deep breath held in cosmic slow motion. As the core grows denser, it begins to spin. That rotation isn't imposed from outside. It's a natural consequence of angular momentum. Every object in space, no matter how still it seems, carries some degree of motion. When a large cloud collapses into a smaller one, that motion has to go somewhere. Like a figure skater pulling in their arms to spin faster, the shrinking cloud spins more quickly as it contracts. But the cloud can't simply keep collapsing evenly, the spin prevents that. Instead, material begins to flatten into a disk around the center. balancing gravity's inward pull with rotation's outward fling. This flattened structure is called an accretion disk, and it's one of the most elegant solutions nature has ever devised. The disk acts as both a funnel and a stabilizer, feeding gas into the forming star while preventing the whole system from tearing itself apart. In the middle, a tiny hot object begins to emerge, the Proto-star. At first, it's hidden entirely from view, wrapped in layers of dust. As it grows, it draws in matter from the disk, each parcel of gas falling inward and releasing energy as it hits the surface. That energy heats the core until it glows faintly in infrared light, still invisible to human eyes but radiant in the right wavelengths. The process is incredibly slow. It can take hundreds of thousands of years for a protostar to gather enough material to ignite nuclear fusion, the process that will eventually define it as a true star. During that time, it continues to pull gas from its surroundings, feeding off the disk that orbits it. This phase is one of balance and tension, gravity pulling inward, pressure pushing outward, rotation keeping everything in motion. It's a delicate dance, and for many young stars it doesn't end quietly. As the protostar grows, it begins to generate jets and bipolar outflows, narrow streams of gas that shoot out from its poles at high speed. These jets can stretch for light years, glowing faintly as they slam into the surrounding material. They act as pressure valves, releasing excess, angular momentum and heat that build up in the disk. Without them, the forming star might collapse too quickly or spin itself apart. To an observer from afar, the scene would be beautiful. A newborn star flinging beams of light and matter into the darkness, carving symmetrical patterns into the nebula around it. It's as if the star is exhaling after a long, deep breath. These outflows also play a role in shaping the larger cloud. They stir the surrounding gas, compressing some areas and clearing others, setting off new waves of collapse. In this way, the birth of one star can trigger the formation of others nearby, a chain reaction that turns a quiet region of space into a busy nursery. The resulting cluster of stars will share a common origin, all born from the same parent cloud, and for millions of years they'll drift through space together like siblings. Meanwhile, inside the forming star, temperatures continue to climb. When the core reaches about 10 million degrees, something extraordinary happens. Hydrogen atoms begin to fuse into helium, releasing vast amounts of energy. This marks the moment the protostar becomes a true star. The energy from fusion pushes outward, balancing gravity's inward pull. The collapse stops, and a steady equilibrium forms. The star stabilizes, no longer shrinking, no longer growing, just burning quietly in its newborn radiance. At this point, the surrounding disk begins to thin. Most of the gas either falls into the star or is blown away by stellar winds. What remains, the heavier dust grains, starts to collide and stick together, forming clumps that grow into pebbles, rocks, and eventually planets. The same process that gave birth to the Sun and Earth is now unfolding in countless young systems across the galaxy. Every twinkle in the night sky represents a success story. A cloud that collapsed, a core that ignited, a fusion fire that caught and held. The entire journey from cold cloud to shining star takes millions of years. To human eyes, that's an eternity. To the galaxy, it's the blink of an eye. Some stars form quickly, massive and short-lived. Others take their time, destined to burn steadily for billions of years. The path they follow depends on mass, temperature, and environment, but the steps are always the same. Gravity gathers, heat builds, fusion begins, and a new light joins the sky. What's remarkable is how each new generation of stars inherits the story of its nebula. The gas and dust that form a star contain traces of everything that came before. The ashes of supernovae, the carbon from red giants, the silicates from earlier systems. Every element heavier than helium was forged in a star that lived and died long ago. When a molecular cloud collapses, it's recycling that ancient material, folding it into something new. In that sense, every newborn star is both the end of one story and the beginning of another. Inside those dark nebulae, where light cannot yet escape, this process is happening continuously. Invisible hands of gravity are sculpting the future night sky. Some of those stars will shine brightly for a few million years before exploding. Others will live quietly for billions, perhaps long enough for life to form on worlds orbiting them. Each one begins the same way, as a soft pulse of density in the deep cold, gathering strength until the first flame of fusion flickers to life. There's a quiet poetry to it all. The universe doesn't rush its work. It builds stars the way wind shapes dunes, slowly, patiently, one particle at a time. And in the end, what emerges is both inevitable and miraculous. A tiny sun glowing against the dark, carrying within it the memory of the cloud that once hid it. Stars, like people, have a way of exhaling at the end of their lives. After spending billions of years quietly fusing hydrogen into helium, a star like our Sun eventually runs out of fuel in its core. With nothing left to counteract gravity, the core contracts and heats up, while the outer layers expand outward into a red giant, swollen, cool and luminous. This is the moment when a star begins to shed its skin. Layer after layer drifts away into space, forming delicate shells of gas. What remains behind is a small exposed core, scorching hot and brilliant, whose radiation illuminates the cast-off layers around it. This fleeting glow is what we call a planetary nebula. The name, as many astronomers like to point out, is misleading. When early observers in the late 1700s aimed their telescopes at these faint round shapes, they thought they resembled distant planets like Uranus or Neptune, small pale disks suspended in the dark. But the resemblance ends there. A planetary nebula has nothing to do with planets. It is the final breath of a dying star, a brief but beautiful display that lasts only a few tens of thousands of years, a blink in cosmic time. The physics behind it is both simple and poetic. As the red giant expands, its outer layers become loosely bound. Stellar winds push this material outward, creating a slow, steady flow of gas. Eventually, the outer envelope becomes detached, leaving behind a dense, compact core, known as a white dwarf progenitor. This tiny remnant, though no larger than Earth, can reach temperatures of over 100,000 degrees. Its ultraviolet radiation strikes the surrounding gas, ionizing it, much like the way a bright lamp makes fog glow. The once invisible shell comes alive with colour, a final luminous sigh before fading into the interstellar medium. Among the most famous examples is the Ring Nebula, or M57, in the constellation Lyra. Even a small telescope reveals its delicate symmetry. A glowing oval suspended in a field of stars with a fainter halo surrounding it. The ring is not truly circular, but a three-dimensional shell seen almost face-on. Inside, gas is expanding outward at roughly 20 kilometers per second, illuminated by the intense radiation of the dying star at its center. Different elements glow in different colors: hydrogen in red, oxygen in green, nitrogen in soft orange. Through spectroscopy, astronomers can read this palette like a code, learning the composition and temperature of the gas. It's not just a pretty shape, it's a map of stellar chemistry painted by light. The symmetry of the Ring Nebula suggests a relatively gentle end, the final exhalation of a stable star. But not all planetary nebulae go quietly. Some, like the Dumbbell Nebula M27 in Vulpecula, show more complex structures. Discovered in 1764 by Charles Messier, the dumbbell appears as two bright lobes connected by a narrow waist, resembling an hourglass, or, true to its name, a weight from an ancient gym. This shape hints at how chaotic the end of stellar life can be. The lobes may form when a star's expelled gas is funneled by magnetic fields or by a companion star in orbit, focusing the outflow into opposing directions. As a result, the nebula expands asymmetrically, creating two luminous wings of ionized gas. In the Dumbbell Nebula, the light we see comes from atoms excited by ultraviolet radiation. Oxygen emits a vivid blue-green glow, while hydrogen and nitrogen contribute red and orange hues. Together, they create a subtle blend that looks almost pastel, a soft watercolour in space. The structure is dynamic, still expanding outward as the central star cools and fades. In another few thousand years, the glow will dim and disperse, the gas merging with the interstellar medium to become the raw material for new stars. Perhaps the most haunting example of all is the Helix Nebula, known affectionately as the Eye of God. It lies just 700 light-years away in Aquarius, making it one of the closest planetary nebula to Earth. Through telescopes, it looks like a giant blue-green iris, with a faint extended halo surrounding it. The helix is actually a series of overlapping shells, a puffed-out spiral of gas viewed almost along its axis. At its centre glows a tiny white dwarf, the exposed remnant of the star that once was. What makes the helix so fascinating are the thousands of tiny cometary knots scattered throughout it. Each knot is a dense clump of gas and dust shaped by the radiation streaming from the central star. The knots trail faint tails pointing away from the light source, like 1,000 miniature comets frozen in motion. They're only about the size of our solar system, yet they number in the tens of thousands, giving the nebula a fine textured appearance, as though it were woven from smoke. These structures are fragile and short-lived, slowly dissolving as the nebula expands. Still, for the brief span of their existence, they reveal the remarkable complexity that light and matter can produce when balanced delicately. The helix is also a kind of preview of our Sun's fate. In about 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus, and perhaps brushing the orbit of Earth. As it sheds its outer layers, it too will form a shell of glowing gas. For a few thousand years, the sky around our dying star will bloom with colour, soft reds and greens drifting outward into space, before fading to black as the white dwarf cools. It's a melancholy vision, but also a comforting one. Even endings can be beautiful. The elements the Sun releases, carbon, oxygen, nitrogen, will go on to seed new stars and planets. In that sense, death is not destruction but renewal. The variety among planetary nebulae is astonishing. Some are nearly perfect spheres, like the Ring. Others are elongated or even butterfly-shaped, such as the Bipolar Nebulae seen elsewhere in the galaxy. Their symmetry often depends on the presence of companion stars, magnetic fields, or the shape of the original stellar winds. Some show multiple shells from episodic ejections, evidence that the dying star shed its layers in pulses rather than in a single event. In every case, though, the mechanism is the same, a star breathing out its last, glowing briefly as its light fades. The colours we see in photographs are not always visible to the human eye, but they carry deep meaning. They represent different wavelengths of emission lines, each corresponding to a specific element. Astronomers use narrowband filters to isolate these lines. Hydrogen alpha for red, oxygen 3 for blue-green, sulfur 2 for orange. When combined, these layers create the vivid, dreamlike images that make planetary nebulae some of the most visually striking objects in the sky. What looks like art is, in fact, chemistry at its most elegant. Planetary nebulae also play an essential role in the galaxy's life cycle. They enrich the interstellar medium with heavier elements, ensuring that the next generation of stars and their planets, will contain the ingredients for complex chemistry and life. Without this recycling, the universe would remain a simple place, filled mostly with hydrogen and helium. Every glowing shell of gas is a contribution to the richness of the cosmos. There's something quietly reassuring about these stellar farewells. Even as a star fades, it still leaves beauty behind. Its light continues to travel across space long after the gas has dispersed. When we point the telescopes toward the ring, the dumbbell, or the helix, we're seeing the echo of a transformation already complete. The star has let go, and in doing so it has become art. One day, far in the future, another civilization may look toward our sun's remnant and see a faint glowing ring, a final whisper of the world that was. They may even give it a name, as we have given names to these others. The ring, the dumbbell, the helix, each one a gentle monument to impermanence, a reminder that even in letting go, the universe still finds a way to shine. Not every dying star fades away in silence. Some, in their final moments, become sculptors, shaping the gas around them into extraordinary forms that defy simplicity. These are the Bipolar and Butterfly Nebulae, objects that look less like the gentle shells of the Ring Nebula and more like explosions captured in motion. Their symmetrical wings stretch across space, delicate yet dramatic, as if a dying star had exhaled in perfect balance. They're among the most striking and mysterious of all nebula shapes, beauty born from chaos, symmetry born from collapse. At first glance, these forms seem too precise to be natural. Long, tapered lobes emerge from a bright central core, often separated by a thin dark waist. The Butterfly Nebula, NGC 6302, is one of the most famous examples. Its twin wings of gas spread out over several light years, glowing in brilliant shades of orange, blue and gold. The central region, invisible in ordinary light, contains one of the hottest known white dwarfs, with surface temperatures exceeding 200,000 degrees. That core acts like a cosmic blowtorch, blasting the surrounding gas with radiation and shaping the nebula into a mirrored pattern that seems both fragile and fierce. The term bipolar refers to this double lobe structure, a pair of opposing outflows aligned along a central axis. Instead of expanding evenly in all directions, as one might expect from a dying star, the gas is channeled into specific paths. Something in the system, perhaps rotation, magnetic fields, or the presence of a companion star, focuses the ejected material into these narrow flows. Over time, the lobes expand and cool, creating the soft, translucent wings we see in telescope images. To understand why these shapes appear, it helps to imagine the star's last moments. As it runs out of fuel, it begins to shed its outer layers, just as in a typical planetary nebula. But in this case, the outflow isn't uniform. The star may be spinning rapidly, creating an equatorial waist, a denser band of gas and dust around its midsection. This waist acts like a dam, blocking the gas from escaping outward in the plane of rotation. The escaping material instead finds easier paths along the poles, shooting out in opposite directions. The result is a pair of jets that gradually sculpt the surrounding gas into long, hollow lobes. In some nebulae, these flows are collimated, meaning they are focused into narrow beams rather than spreading out. This focusing can happen through magnetic fields that guide the motion of charged particles, or through the gravitational influence of a companion star. The outcome is astonishing precision. Some bipolar nebulae have jets that remain straight and stable for light years, while others curve gently like ribbons caught in a slow breeze. Each pattern tells a story about the forces at play around the dying star, about rotation, magnetism and companionship. The Butterfly Nebula shows this process in its most theatrical form. The gas in its lobes is moving at hundreds of kilometers per second, carrying with it the chemical traces of the star's final outbursts. The inner regions are rich in ionized oxygen and nitrogen, glowing brightly under the flood of ultraviolet light from the central star. Closer to the equatorial waist, dust absorbs and scatters that light, creating dark bands that slice across the nebula's glowing wings. It looks peaceful in still images, but the reality is dynamic, a storm of motion stretched across millennia. Another striking example is the Twin Jet Nebula, or PNM2-9, which could easily be mistaken for a cosmic butterfly in flight. Its two symmetrical lobes extend outward in perfect opposition, each tipped with faint knots of glowing gas. At its centre lies not one star, but two. A binary pair locked in orbit. As the dying star sheds its outer layers, the companion's gravity shapes the flow, channeling material into a spiral before it's flung outward along the poles. This interaction creates a remarkable symmetry so precise that the nebula looks almost engineered, yet it's all the result of natural physics, gravity and momentum performing their quiet duet. The presence of a binary companion is one of the leading explanations for these elegant forms. When two stars orbit close together, their gravitational dance distorts the outflowing gas, focusing it into cones or jets. The interaction also helps the dying star lose mass more efficiently, producing multiple shells or hourglass shapes. In many bipolar nebulae, careful measurement of motion reveals subtle asymmetries, one lobe slightly larger, one side brighter, tiny imperfections that betray the influence of a partner star. In this way, symmetry itself becomes a clue. When astronomers see wings this even, they suspect there's a hidden companion steering the wind. Magnetic fields also play a quiet but crucial role. As the star rotates, its magnetic field lines twist and stretch, channeling ionized gas along their paths. These invisible threads help maintain the structure of the outflows, keeping them coherent even as they travel vast distances. In the glowing wings of the Butterfly Nebula, faint filaments trace where these fields once guided the gas, nature's calligraphy written in plasma. What's fascinating is how these forces combine to produce such variety. Some bipolar nebulae are narrow and elongated, like jets frozen in time. Others are wide and soft with rounded lobes that look almost like bubbles. Still others display multiple pairs of wings, evidence of episodic ejections, bursts of material thrown off at different times and directions. The shapes are not random, they're records, three-dimensional diaries of a star's final centuries. Viewed in infrared or radio light, the hidden complexities multiply. Dust lanes cut across the glowing gas, forming intricate lattices. Shock fronts, the boundaries where fast winds collide with slower ones, create ripples that spread outward like the rings of a pond. In some nebulae, astronomers can trace these features to specific moments in time, mapping out a chronology of the star's dying breaths. It's both art and archaeology, studying patterns of beauty to uncover patterns of physics. Even the colour of these nebulae tells part of the story. In visible light, the lobes often appear blue or teal from oxygen emission, while the denser waste glows red with hydrogen and sulfur. The combination gives them a layered, almost iridescent look, a cosmic butterfly shimmering against the dark. Each hue is a signature of temperature, density and composition. The cool outer regions glow softly, while the inner edges burn with sharp brilliance, marking the boundary between chaos and calm. Over time the symmetry fades. The lobes expand, their edges blur, and the central star cools into a white dwarf. The wings that once glowed so brightly drift apart and dissolve into the interstellar medium. Yet for the short time they exist, it's perhaps 20,000 years no more, they remind us how intricate the universe can be, even in its farewells. If you could drift slowly through one of these nebulae, the view would be astonishing. A bright core ahead, twin arcs of colour curving outward on either side, and thin filaments spiralling away like strands of silk. Every direction would lead to balance, every motion mirrored somewhere else. It's a scene that feels purposeful, even though it's born entirely from physics, the result of forces seeking equilibrium. There's something soothing about this cosmic symmetry. It suggests that even in collapse, the universe strives for order. The wings of a dying star may not flutter, but they carry the same grace, a final act of balance before fading into stillness. The butterfly shape is no accident of imagination. It's the geometry of farewell, written in light and motion, unfolding slowly in the quiet of space. Nearly 1,000 years ago, in the summer of 1054, a new light appeared in the sky. It was bright enough to be seen in daylight, casting shadows at night and startling the people who watched the heavens closely. Chinese and Arab astronomers recorded it carefully, noting that it stayed visible for weeks before fading. What they were seeing was the death of a massive star, a supernova, so luminous that it briefly rivaled the moon. When the light finally dimmed, the star was gone, replaced by a faint, ghostly cloud. Today, we call that remnant the Carina Nebula, catalogued as M1, the first entry in Charles Messier's famous list of celestial curiosities. To the eye of a telescope, the crab looks like a tangled web, filaments of glowing gas woven into a delicate network, expanding slowly into the darkness. It is both chaotic and organized, a burst of energy frozen in mid-motion. The explosion that created it released more power in a few seconds than the sun will emit in its entire lifetime, and yet what remains now feels almost gentle, a lacework of colour adrift in space. The nebula is still growing, its tendrils stretching outward at nearly 1,500 kilometers per second, a silent expansion that continues nearly a millennium after the blast. At its core lies something extraordinary, the collapsed heart of the original star, now transformed into a neutron star only about 20 kilometers wide. This object, known as the Crab Pulsar, spins 30 times per second, sending out pulses of radio waves, X-rays and visible light with clockwork precision. It's a cosmic lighthouse, its beams sweeping across space as it rotates. Each pulse marks another turn, another reminder that the energy of a supernova doesn't simply vanish. It changes form, from fire to rhythm. The heartbeat of this tiny remnant powers the entire nebula around it. The glow we see from the crab isn't just from hot gas. Much of its light comes from synchrotron radiation, a phenomenon that occurs when charged particles spiral through magnetic fields at nearly the speed of light. The result is a continuous glow that spans the spectrum from radio waves to gamma rays, painting the nebula in hues that shimmer and fade across wavelengths. This synchrotron light gives the crab its distinctive diffuse luminescence, a soft veil of energy overlaying the intricate filaments of gas. It's as though the whole structure hums with quiet electricity, powered by the spinning heart at its centre. Those filaments themselves are the visible remains of the star's outer layers, fragments of hydrogen, helium, oxygen, nitrogen, and heavier elements torn apart by the explosion. Each thread carries a record of the event, how fast it was ejected, how it interacted with the shockwave, how it cooled and recombined. Some filaments glow red from hydrogen emission, others shine green with oxygen, or blue with sulfur. Together they form a palette of elements, proof that even in death, a star enriches the universe around it. That enrichment is more than poetic, it's essential. The Carina Nebula, like all supernova remnants, is part of the galaxy's recycling system. The explosion scattered newly forged elements into space, carbon for life, calcium for bones, iron for blood, silicon for stone. The atoms in our own bodies were once inside stars like the crab's progenitor, fused in their cores and then flung outward to become the raw material of planets and people. Every supernova writes a chemical signature into the Milky Way, ensuring that each generation of stars and worlds is richer than the last. The Carina Nebula's structure tells us a great deal about how that process unfolds. Its expanding shell, roughly 10 light-years wide, is filled with filaments that move at different speeds, tracing the shock front from the original explosion. The inner regions are filled with a smooth, glowing plasma energized by the pulsar's radiation, while the outer filaments form a fragile cage around it. Astronomers can measure the motion of these threads directly, comparing old photographs to modern ones and watching the faint drift of each wisp year by year. It's one of the few places in the sky where the passage of time is visible. If the crab seems calm now, that's only because we're seeing it through the lens of patience. The original explosion was unimaginably violent. When the star's core collapsed, gravity crushed matter so tightly that protons and electrons merged into neutrons, creating a sphere of pure nuclear density. The shockwave rebounded outward, blasting the outer layers into space and igniting a burst of radiation that briefly outshone the entire galaxy. Yet even that fury wasn't wasteful. It was the universe's way of redistributing its ingredients. What looked like destruction was simply transformation. In the center of the nebula, the pulsar wind, a steady outflow of high-energy particles, keeps the entire structure glowing. This wind pushes against the surrounding gas, forming ripples and knots that change over time. Images taken just years apart show wisps moving outward from the core, almost like waves expanding across a pond. The pattern is mesmerizing, a continuous interplay between the pulsar's magnetic field and the nebula gas, shaping and reshaping the filaments. The crab is not static, it's alive with motion, though on timescales that are both swift and slow. Astronomers studying the crab use it as a laboratory for physics under extreme conditions. The magnetic fields near the pulsar are trillions of times stronger than Earth's. The rotation is so fast that a single teaspoon of its material would weigh 1 billion tons. Yet for all that intensity, the Crab Nebula remains a source of calm fascination rather than drama. It is the very definition of controlled chaos, the energy of a cosmic catastrophe slowed and softened into a sculpture of light. Viewed through different instruments, the nebula reveals new faces. In radio waves it appears vast and diffuse, tracing the synchrotron glow of electrons moving through magnetic fields. In optical light we see the detailed filaments, twisting and branching like veins. In X-rays, the pulsar dominates, surrounded by a compact, high-energy torus, a luminous donut of radiation that marks the inner engine. Each wavelength tells part of the story, and together they form a complete portrait of stellar death turned into art. There's a quiet rhythm to it all, the pulsar's steady beat, the slow expansion of the filaments, the cooling of the gas. Every part of the crab moves at its own tempo. The result is a kind of cosmic music, played across scales of time and energy that defy human sense, but feel intuitively harmonious. The nebula may look fragile, but it carries within it the power of 1,000 suns and the memory of an ancient explosion witnessed by humankind long before telescopes existed. To gaze at the crab is to see both the past and the future. The light we see tonight began its journey nearly 7,000 years ago, long before that final flash reached Earth in 1054. The explosion had already happened, its debris was already spreading across the galaxy, and long after the pulsar's heartbeat finally slows, the elements it cast into space will drift onward, forming new clouds, new stars, and new worlds. So the Crab Nebula is not a symbol of destruction, but of continuity. A star's death becomes a nebula's birth. A brief flash becomes a long, lingering glow. The pulsar's ticking is not an ending, but a metronome, a reminder that even in the silence of space the rhythm of creation continues. It's the universe taking a deep breath after a great outburst, and then exhaling softly into eternity. When a massive star dies in a supernova, the explosion is brief, a few heartbeats of unimaginable power. But its aftermath lingers for tens of thousands of years, spreading outward like ripples from a stone dropped into still water. Over time, those ripples cool and thin until they become translucent waves of colour, glowing faintly where shock fronts meet interstellar gas. Two of the most beautiful examples of this cosmic embroidery are the veiled Nebula in Cygnus and the Vela supernova remnant in the southern sky. They are what happens when the universe decides to turn an explosion into art. The Vela Nebula lies about 2,400 light-years away, and it's all that remains of a star that exploded somewhere between 5 and 10,000 years ago. Today, what we see is not a solid shell, but a lacework of filaments, thin sheets of gas seen mostly edge-on. Each filament is a shock front, where the expanding blast wave from the supernova ploughs into the surrounding interstellar medium. The collision compresses and heats the gas, stripping electrons from atoms and causing them to glow in vivid colours. In photographs, these filaments resemble fine silk threads stretched across space, red from hydrogen, green from sulfur, blue from oxygen, all delicately layered against the blackness. It's easy to forget that these glowing curtains are enormous. The entire Vela complex spans more than 100 light-years across, about 10 times the distance between the Sun and its nearest stellar neighbour. Yet its features are so thin that in places they are only a fraction of a light-year wide, like smoke frozen in time. The most famous portions have their own names: the Eastern Veil, a rippling arc like a pale flame, the Western Veil, known also as the Witch's Broom, and Pickering's Triangle, a tangle of luminous threads that looks less like destruction and more like cosmic calligraphy. What we're really seeing is shock physics written in colour. As the supernova's shock wave moves through space, it compresses the gas ahead of it to millions of degrees, exciting atoms until they emit light. Where we look directly into the front, the emission appears diffuse and soft. Where we see it edge on, the view sharpens into fine filaments. The different colours correspond to different temperatures and atomic species. Hydrogen glows red, oxygen blue-green, sulfur orange, the nebular equivalent of embroidery threads, each hue recording a specific energy. In a sense, the universe does embroidery, sewing together speed, heat, and chemistry into something quietly intricate. The Vela's beauty also lies in its motion. Though it seems still, astronomers can detect its slow expansion even within a human lifetime. By comparing images taken decades apart, they can watch the filaments drift outward, the whole structure gradually ballooning into space. In another few thousand years, the threads will fade as the gas cools and mixes with the interstellar medium, its once distinct pattern merging back into the fabric of the galaxy. But for now, we catch it mid-stitch, the delicate phase where energy and elegance coexist. Farther south, in the constellation Vela, lies another supernova remnant, older, closer, and even grander in scale. The Vela supernova remnant sprawls across an area of sky more than 8 times wider than the full moon. At a distance of only about 800 light-years, is one of the nearest supernova remnants to Earth, though it's faint enough that its full extent can only be seen in long exposures. What the telescope reveals is a chaotic tangle of filaments and arcs, overlapping and interwoven, the aftermath of a massive star that exploded roughly 11,000 years ago. The Vela remnant is so large and diffuse that it can be hard to take in as a single object. Its edges curl into looping arcs, some bright, some barely perceptible. In places, they overlap with other remnants, such as the Gum Nebula, creating layers of texture that make the region look almost three-dimensional. The filaments here glow for the same reason as those in the Veil. They mark the shock fronts where the expanding debris from the explosion slams into surrounding gas. But because Vela is closer, we see its structure in greater detail. Bright knots, ripples, and faint wisps that trace the flow of energy outward from the invisible centre. At that centre lies the Vela Pulsar, the compact neutron star left behind by the original supernova. It spins 11 times per second, emitting pulses of radio waves and gamma rays. The energy it releases helps keep the nebula glowing, but it's a quieter engine than the one in the Crab Nebula. Its rhythm is steady, its output subdued, a cosmic heartbeat that continues to tick long after the explosion has faded. Around it, the gas and dust expand slowly into space, each filament a thread of history stretching back 10 millennia. One of the remarkable things about remnants like Vela and the Veil is how different they appear from their explosive origins. A supernova is a moment of violence, a flash that outshines entire galaxies for a brief time. Yet what follows is soft, structured, and patient. The shockwave moves outward, but its front is thin and uneven, shaped by the texture of the interstellar medium it encounters. Dense pockets of gas slow the wave, empty regions let it race ahead. The result is a web of folds and curls, much like wind blowing through thin fabric. The physics may be fierce, but the outcome is grace. If you look closely at images of the Veil, you can almost trace the path of motion, the arcs where shock fronts intersect, the loops where turbulence creates knots. Each line marks the boundary between fast-moving hot gas and slower, cooler material. At those boundaries, atoms are stripped, excited and recombined, producing the emission lines we detect. Astronomers call this radiative shock emission, but the name hardly captures its subtlety. It's more like light stitched into the night, the slow unravelling of a star's final gesture. The same story plays out in the Vela remnant, but on a grander, messier scale. Because it's closer and older, the filaments have had more time to twist and disperse. In some places they form loops as large as 10 light-years across, in others they fade into barely visible haze. Radio observations reveal expanding shells and filaments that are still moving outward at hundreds of kilometers per second. If we could speed up time, we'd see a vast bubble breathing slowly in and out, reshaping itself as it interacts with the galaxy around it. From a scientific perspective, both the Veil and Vela remnants are laboratories for understanding how energy moves through space. They show how shock waves compress gas, how magnetic fields guide particles, and how heavy elements from the explosion mix into the surrounding medium. But beyond the physics, they are also reminders of continuity. The atoms glowing in these filaments will someday become part of new stars, planets, or perhaps living beings. The lace of light we see is not an ending, but a step in a cycle, an embroidery pattern that will be unpicked and re-sewn many times over cosmic history. For stargazers, the Veil and Vela are studies in contrast. The Veil, delicate and narrow, seems like a veil in motion, fine, fragile and distant. The Vela remnant, sprawling and tangled, feels closer, almost too vast to comprehend. One is a whisper, the other a sigh. Yet both tell the same story, that destruction can leave behind beauty, and that even the most violent events in the universe eventually settle into elegance. When we look at these remnants through a telescope or a photograph, we're seeing energy made visible, the ghost of motion, the residue of brilliance. The Veil glows in the north like a frozen ripple of silk, while Vela drifts through the southern sky as a tapestry of light and shadow. They are reminders that time in the cosmos is slow and kind, that even an explosion can end in grace, and that the universe, for all its power, still finds time for a little embroidery. If the Milky Way were a city, then the Tarantula Nebula would be the bright industrial district just beyond its limits, vast, busy, and forever awake. It lies not in our own galaxy, but in the Large Magellanic Cloud, a small satellite galaxy that orbits the Milky Way about 160,000 light-years away. Through telescopes, the tarantula is unmistakable, a sprawling, luminous web of gas and dust, glowing with the energy of countless newborn stars. It's the most active star-forming region in our galactic neighbourhood, and one of the largest known anywhere. At first glance, the Tarantula Nebula, also called 30 Doradus, looks like an explosion caught mid-breath. Long tendrils of gear radiate from a dense central core, forming a pattern that to early astronomers resembled the legs of a spider. But where an earthly spider spins silk, this one spins light. Its filaments are the result of immense feedback, radiation, winds, and shock waves from massive stars carving cavities into the surrounding gas. The result is a structure both fierce and fragile, like a honeycomb sculpted by lightning. At the centre of this cosmic hive lies the R136 cluster, a gathering of some of the most massive and luminous stars known. Many of them exceed 100 times the mass of the Sun, and their combined output is staggering. Together, they shine millions of times brighter than our entire solar system, flooding the nebula with ultraviolet radiation. That radiation ionizes the surrounding hydrogen, making it glow in shades of scarlet and gold. Meanwhile, fierce stellar winds, streams of charged particles moving at thousands of kilometers per second, crash into nearby gas, compressing it into new knots and filaments. It's a perpetual feedback loop. Energy creates structure, structure triggers new stars, and those stars unleash more energy. The Tarantula's environment is a perfect storm of creation. Within just a few hundred light years, thousands of stars are being born, many of them in clusters so dense that their light blends into a single glare. This makes the region an invaluable window into how galaxies form stars on grand scales. In the Milky Way, our view of star-forming regions is often obscured by dust, but the Tarantula sitting above the plane of our galaxy offers a clear, panoramic view. Here, we can watch the process unfold in high resolution, the interplay between gravity pulling gas inward and radiation pushing it outward, a cosmic tug-of-war that defines the life of every galaxy. The nebula's vast cavities and ridges are shaped by this tension. Each cavity is a bubble carved out by stellar winds, its walls glowing from the heat of nearby stars. Over time, these bubbles merge, forming networks that look like honeycomb cells stitched together. Within the dense walls of those cells, new stars begin to form, their birth triggered by the compression of gas. The process is so efficient that astronomers sometimes describe the Tarantula as a galactic heartbeat, its rhythm marked by waves of creation pulsing outward from the centre. One of the most remarkable aspects of the Tarantula Nebula is how it serves as a bridge between the familiar and the extreme. On one hand, the same basic processes are at work here, as in smaller nebulae like Orion or Carina. Gravity, radiation, and magnetic field shaping gas into stars. On the other hand, everything happens on a far larger scale. The sheer density of massive stars in R136 pushes those processes to their limits, producing temperatures, pressures, and luminosities that test the boundaries of physics. Some of the stars in this cluster are so energetic that they are already losing mass through powerful outflows, destined to end their lives in spectacular supernovae, or perhaps even to collapse directly into black holes. Astronomers have described the Tarantula as a mini starburst region, a scaled-down version of the intense star formation seen in entire galaxies. In such places, galaxies essentially breathe. Their gas clouds collapse into bursts of star formation, releasing energy and radiation that sweep away surrounding material, temporarily halting further collapse. Over time, the gas cools and settles again, beginning a new cycle. The Tarantula shows this process in miniature, giving us a living example of how galaxies regulate themselves, how they inhale, ignite, and exhale. Looking closely at the nebula, you can see these layers of motion everywhere. Bright ridges mark the walls of expanding bubbles. Dark filaments trace where cooler gas still resists the pressure of radiation. Here and there, faint arcs of shock-heated gas reveal where fast winds have collided head-on. The entire region hums with invisible energy, radio waves, X-rays, and ultraviolet light all blending into a single quiet roar of activity. To the human eye it appears serene, but the tarantula is anything but calm. It's a stellar nursery in overdrive, a place where gravity and energy race each other to the finish line. The tarantula's influence extends far beyond its own boundaries. The collective outflows from its stars drive vast streams of material into the surrounding galaxy, enriching it with heavier elements and stirring the interstellar medium. This feedback shapes how the Large Magellanic Cloud evolves, much as similar regions have sculpted the Milky Way over time. In this way, the tarantula acts as both an artist and an engineer, decorating its surroundings with beauty while quietly redrawing their structure. When we observe it from Earth, we are looking back in time by 160,000 years, long before humans began to record history. The light we see tonight left when our ancestors were still learning to paint on cave walls. In that sense, the tarantula is a time capsule, preserving a moment in the life of another galaxy, yet it's also a mirror. By studying it, astronomers learn how our own galaxy once looked, when regions like Carina and Orion were still in their prime. Every bright knot and filament tells us something about the way the Milky Way formed its stars and continues to evolve today. In the heart of the tarantula, the R136 cluster stands as a testament to what gravity can do when left unchecked. The combined winds from its stars are powerful enough to shape an entire region of space more than 1,000 light-years across. The cluster itself is less than 2 million years old, a blink in cosmic terms, and yet it has already begun to change its environment. The ultraviolet light streaming from its members ionizes the surrounding hydrogen, turning it into a glowing sea of plasma. Within that sea, new stars continue to emerge, forming smaller groups that orbit and interact like eddies in a river. For astronomers, the Tarantula Nebula is both a laboratory and a storybook. It shows in exquisite detail how stars form, interact, and eventually reshape their surroundings. But it also tells a larger story about the rhythm of galaxies, about how energy and matter cycle endlessly between clouds and stars. The same laws that govern this colossal region also govern the faint patches of gas scattered through our own Milky Way. By studying something so far away, we come to understand what's happening right next door. In a few million years, many of the massive stars in the tarantula will explode as supernovae, just as others did before them. Those blasts will send ripples through the nebula, compressing new gas and sparking another wave of star formation. The pattern will continue generation after generation as the Large Magellanic Cloud slowly evolves. From a distance it will appear as a steady glow, but up close it's a living, breathing system, a galactic lung inhaling and exhaling through the language of light. So when we gaze at the tarantula, we're not just looking outward, we're looking homeward too. The same processes that light up that faraway galaxy once shaped the Milky Way, and one day they will shape it again. The nebula's tangled web of stars and gas is a reminder that the universe is not static but alive, a network of creation constantly renewing itself. The tarantula spins its threads across another galaxy, but those threads reach all the way here, weaving our story into the same cosmic fabric. The deeper you look into a nebula, the more you begin to realize that space is not empty at all. Between the stars, in the darkness where visible light fades, the universe is quietly busy with chemistry. There, inside the cold molecular clouds, atoms and dust grains come together to form molecules, simple ones like carbon monoxide and water, and more complex chains that hint at the raw materials for life. It's not a chaotic chemistry set, but a slow, patient process guided by time, temperature, and chance. This is the hidden laboratory of the cosmos, where matter practices the art of becoming interesting. The first clues to this chemistry came from a molecule so common it now serves as a kind of cosmic signpost: carbon monoxide, or CO. In visible light, molecular clouds are dark, but in radio waves, CO glows faintly. Astronomers use this glow to map where cold gas hides. Hydrogen, the most abundant element in the universe, is hard to detect directly at such low temperatures. Its molecules are nearly invisible. But carbon monoxide, with its gentle rotational transitions, radiates at wavelengths that radio telescopes can easily pick up. So when astronomers trace CO, they're really tracing hydrogen by proxy, sketching the outlines of the cold reservoirs where stars will one day form. The picture that emerges is beautiful in its understatement. Vast clouds of molecular gas, quietly drifting through spiral arms, their interiors cold enough for atoms to stick together. At temperatures just a few dozen degrees above absolute zero, collisions between particles are rare but meaningful. Hydrogen binds with oxygen to form H2O, carbon meets oxygen to make CO and CO2, and on the surfaces of tiny dust grains, new reactions begin, slow-motion chemistry happening one atom at a time. These grains are the countertops of the interstellar kitchen, and each one carries a thin coating of ice mantles, composed of frozen water, carbon dioxide, ammonia, and methanol. Within those icy shells, the chemistry becomes surprisingly complex. When ultraviolet light or cosmic rays strike the ice, they break molecular bonds, allowing the fragments to recombine into new arrangements. Over millions of years, this quiet photochemistry can produce organic compounds, alcohols, simple sugars, and long carbon chains. These are not yet the molecules of life, but they are the first whispers of possibility. Meteorites that fall to Earth still carry some of these same compounds, fossilized relics of the chemistry that happened long before the Sun was born. In the infrared, these molecules reveal themselves through faint, distinctive signatures, patterns of absorption and emission that act like fingerprints. Among the most intriguing are the polycyclic aromatic hydrocarbons, or PAHs. These are flat, ring-shaped molecules made of carbon and hydrogen, similar in structure to the soot from a candle flame. They form wherever carbon-rich gas cools, in the envelopes of dying stars, in the interstellar medium, even in the outflows of galaxies. When ultraviolet light hits them, they fluoresce, releasing energy at specific wavelengths in the mid-infrared. The result is a set of glowing bands that astronomers can identify across the cosmos. These PAH bands are so reliable that they're used as tracers for star formation. Where they glow, young stars are often nearby, their ultraviolet radiation stirring the molecular gas around them. The presence of these aromatic molecules also links the story of stars to the chemistry of life. On Earth, similar carbon ring structures form the backbone of many biological compounds. The idea that the same kinds of molecules drift between stars gives a comforting sense of continuity, a hint that nature may follow similar recipes everywhere it can. Because much of this activity happens deep inside cold clouds, ordinary optical telescopes can't see it. Visible light simply doesn't make it through the dust. But in infrared and radio, the darkness opens. The wavelengths are longer, allowing them to slip through the fine grains that block shorter light. That's why observatories like Spitzer, ALMA, and the James Webb Space Telescope have become the chemists' instruments of choice. They don't look for shapes or colours, they listen for vibrations, for the faint hum of molecules stretching and twisting in the cold. Each frequency corresponds to a specific chemical bond, so by reading the light, astronomers can identify what's out there, molecule by molecule. When Spitzer mapped the Milky Way in the mid-infrared, it revealed an unexpected richness, glowing bands of PAHs tracing the spiral arms like neon lights. ALMA, the Atacama Large Millimeter/Submillimeter Array, took things further, detecting complex organic molecules in the disks of young stars, methanol, formaldehyde, even ethyl alcohol. And now the James Webb Space Telescope is bringing those same regions into focus with unprecedented clarity, showing icy grains and molecular emissions in fine detail. What was once a black void has become a vibrant, whispering world, full of signals waiting to be decoded. The chemistry of these clouds is slow, but it's relentless. Over millions of years, simple molecules give rise to more intricate ones. Dust grains act as catalysts, allowing reactions that would never occur in the thin gas of space to happen on their surfaces. When a new star forms, its heat evaporates the surrounding ice, releasing those accumulated molecules back into space. Some are destroyed, others reform in new combinations. The material then mixes into new generations of clouds, spreading its chemical heritage across the galaxy. It's easy to think of this as kind of cosmic alchemy, the slow transformation of simplicity into complexity. Hydrogen, helium, and a pinch of carbon are all that's needed to begin. But through endless repetition, the universe builds molecules that can store energy, absorb light, and eventually in the right places participate in biology. Each molecule is a tiny milestone on that journey. Water freezes and melts, methanol condenses, ammonia mixes, and carbon chains lengthen, forming the molecular scaffolding that might one day host living chemistry. In many nebulae, these molecules glow faintly in infrared light, like embers beneath the visible fire of starlight. The famous Orion Nebula, for instance, is filled not only with young stars but also with rich molecular gas and glowing PAH bands. Viewed through an infrared telescope, its dusty clouds become translucent, revealing intricate filigrees of emission that mirror the dance of molecules at work. It's the same in the dark clouds of Taurus and Ophiuchus, where star formation is just beginning, places invisible to the naked eye but alive in the infrared, full of chemical promise. What's particularly fascinating is how much of this chemistry happens without any direct human intuition. In laboratories on Earth, we think of reactions as needing heat, catalysts, or containers. In space, the containers are dust grains, the catalysts are cosmic rays, and the heat is supplied sparingly, one photon at a time. Yet the outcome is recognizable. It's as if nature, given enough time, finds its way toward complexity, regardless of the conditions. These molecular clouds are not merely star factories, they're chemical archives. They preserve the history of every reaction, every element forged in the hearts of older stars. When we study them, we're not only looking at how matter behaves in space, but also at how the building blocks of life are distributed across the galaxy. The same ices that coat dust grains here have been detected in comets and meteorites that fall to Earth, linking our planet's chemistry directly to the interstellar medium. In the end, the chemistry of the dark is a lesson in patience. Molecules form slowly, survive briefly, and yet leave lasting marks. Each step, from carbon monoxide to PAHs to complex organics, is part of a long chain of creation that spans billions of years. We may never see it happening in real time, but its fingerprints are everywhere, in the spectra of nebulae, in the ices of comets, and perhaps ultimately in the molecules that make up life itself. The night sky, seen in visible light, tells a story of energy, of stars burning and galaxies shining. But seen in infrared and radio, it tells another story, one of chemistry and connection. There, in the coldest and quietest places, atoms are learning to dance together, slowly, persistently, and beautifully. The universe is writing its recipes in the dark, one molecule at a time, and those recipes may one day be the reason something out there opens its eyes and looks back. Every nebula has its season. For a while it glows with energy, the soft light of ionized gas. the heat of newborn stars, the shimmering colours of dust. But sooner or later, even the most vibrant cloud begins to fade. The same stars that brought it to life eventually unmake it, pushing away the gas and dust that once hid them. What's left behind is not emptiness, but a new arrangement, a cluster of stars set free, drifting slowly away from the nursery that created them. This transformation from cloud to cluster is the natural conclusion of star formation. When a molecular cloud collapses, it rarely does so all at once. Only a fraction of the gas ever becomes stars. The rest remains as diffuse material, warmed by starlight, stirred by winds, and eventually dispersed back into the galaxy. Astronomers call this the star formation efficiency, and it's surprisingly low. Even in the busiest stellar nurseries, only about 10% of the available gas ends up locked inside stars. The rest escapes, recycled for another generation. The universe, it seems, is more patient than productive. As the first massive stars ignite, they begin to reshape their surroundings almost immediately. Their radiation ionizes the surrounding hydrogen, turning it into glowing plasma. Their winds carve out cavities, pushing gas into arcs and filaments. Over a few million years, this feedback adds up. The combined energy of dozens of young stars, especially the heavyweights with short lives and big personalities, creates a kind of internal pressure cooker. The nebula inflates like a balloon, and eventually the gas can no longer hold together. When the pressure overcomes gravity, the cloud breaks apart and its material is blown into interstellar space. This event is sometimes called gas blowout, and though the phrase sounds dramatic, the process is almost gentle by cosmic standards. The nebula doesn't explode, it exhales. Over hundreds of thousands of years, the gas drifts away, dimming the once luminous region. The newly formed stars, now unshrouded, shine freely into the galaxy. What remains of the cloud becomes a faint, translucent wisp before dispersing entirely. The nebula, as an object, ceases to exist. What's left behind is the cluster, a family of stars bound together by gravity, at least for a while. These clusters vary enormously in size and character. Some are compact and tight-knit, like the Pleiades or the Hyades. Others are loose associations destined to drift apart after just a few 100 million years. Their fate depends on how much mass they share and how strongly they are bound. The stars within them range from faint red dwarfs to brilliant blue giants, arranged by a quiet but consistent rule known as the stellar initial mass function. This mass function is, in essence, a cosmic census. It describes how many stars of each mass a typical cloud produces, and it's surprisingly predictable. For every massive star, dozens of smaller ones form, and hundreds of even smaller red dwarfs. The distribution follows a pattern that repeats across different regions of the galaxy, as if the universe uses the same formula everywhere. The result is a population shaped not by chance, but by balance. A few bright, short-lived giants to enrich the cosmos, and many small, enduring stars to keep it shining steadily for billions of years. The giants are the architects of change. Their brief, brilliant lives end in explosions that scatter heavy elements back into space. Oxygen, carbon, iron, silicon. The same ingredients that will later become part of new nebulae, planets and living things. The smaller stars, meanwhile, contribute stability. They burn slowly, living for tens or even hundreds of billions of years. Their light a quiet background hum that keeps galaxies glowing long after their larger siblings have died. Together they form the galaxy's long-term economy, bright investments that pay off in metals, and steady ones that preserve energy and light. In the early days of a young cluster, the stars remain close together, still feeling the pull of their shared gravity. From afar they resemble a swarm of fireflies, dense, vibrant, and newly liberated from their cloudy cradle. But time and motion have no sympathy for permanence. As the cluster orbits the galactic centre, tidal forces stretch and scatter it. Encounters with other stars or clouds can disturb its balance, and little by little, members drift away. After a few 100 million years, only a faint trace of the original group remains. The stars continue their journeys alone, scattered across the galaxy like seeds on the wind. It's easy to think of this dispersal as an ending, but in truth, it's just another turn in the cycle. The gas that was expelled during the nebula's blowout doesn't disappear. It becomes part of the interstellar medium, the vast reservoir of diffuse material that fills the galaxy. Over time, supernova shocks, stellar winds, and galactic tides stir this gas, compressing it in places, thinning it in others. Eventually, new clouds form, denser, cooler, and ready to begin the process again. The death of one nebula becomes the birth of another. In this sense, the galaxy functions like a vast recycling system. Nothing is truly lost, only transformed. The efficiency of this system is remarkable. When a star dies, the heavy elements it releases enrich the gas around it, altering the chemistry of the next generation of stars. Each cycle leaves the galaxy slightly more complex, richer in metals, dust, and potential. Early stars in the Milky Way were composed almost entirely of hydrogen and helium, but each successive wave of star formation has added new ingredients. The clouds that form today are filled with the debris of countless earlier generations. In a very real sense, every atom in your body was once part of this endless loop, born in a star, scattered in a nebula, and eventually gathered into something new. When the gas disperses and the light fades, the beauty of the nebula doesn't vanish, it migrates. It lives on in the glow of stars that were once hidden inside it, in the subtle metals that colour their light, and in the molecules drifting between them. The clouds may dissolve, but their story continues in every corner of the galaxy. The bright arcs of the Orion Nebula, the filaments of Carina, the faint tendrils of the Rosette, all of them are chapters in the same ongoing narrative, the slow exchange of matter between darkness and light. Over billions of years, this process has built everything we see. Galaxies evolve not through sudden events, but through steady cycles of creation and dispersal. Each phase, cloud, cluster, dispersal, feeds the next. Some regions flare with activity, while others rest in quiet between bursts. It's not unlike breathing. The galaxy inhales gas to form stars, exhales energy to spread it back out, and repeats the motion endlessly, balancing growth and renewal. To watch a nebula fade is to witness that breath in reverse. The brilliant light dims, the colours soften, and the gas recedes into the night. Yet what seems like loss is really transformation. The same atoms that once glowed red in hydrogen emission may someday blaze inside a new star or shimmer in the atmosphere of a distant planet. The matter never stops moving, it only changes address. Even the clusters themselves carry echoes of their origins. Many of the bright stars we see in the night sky, Sirius, Vega, Altair, once belonged to clusters that have long since dissolved. Their siblings are scattered across the galaxy, invisible to the naked eye but traceable through their shared chemistry and motion. The stars remember, even if the nebula does not. And so the circle closes, gas becomes stars, stars reshape the gas, the remnants drift and reform. The galaxy is a living system, not static but ever-renewing. Every glowing nebula is a momentary bloom in a much longer cycle, a spark between breaths. When its light finally fades, the quiet that follows isn't emptiness, it's potential. The same darkness that once gave birth to light is preparing to do so again, waiting patiently for gravity, time, and chance to weave the next bright cloud from the ashes of the old. Nebulae are not just ornaments in the sky, They are the universe at work, clouds of gas and dust where light and matter meet, where energy becomes colour, and where endings quietly turn into beginnings. Each hue is a clue to the physics within: hydrogen glowing red from warmth, oxygen shining blue with energy, sulfur whispering orange along the edges of change. Every shape tells a story, a pillar sculpted by starlight, a ring formed by farewell, a filament stretched thin by time. What looks like chaos from afar is, up close, a calm conversation between creation and decay. Across all these clouds, from the glowing tendrils of Orion to the ghostly lace of the veil, a pattern emerges. The same patient cycle repeated everywhere. Gas collapses into stars. Stars light and sculpt the cloud. And when they die, their remnants scatter back into the dark, seeding the next generation. It's not destruction, it's renewal, steady and sure. Nebulae are how the universe tidies itself, sweeping up old light, folding it into new forms, and keeping the galaxy breathing. Perhaps that's the quiet comfort they offer. Even in the grandest scales of time, nothing is wasted. What fades will return. What burns away will glow again, reshaped and reborn. The universe is always cleaning up after itself, polishing the dust, rearranging the stars, and starting fresh. So as the last light of this journey drifts away, let your thoughts slow with it. Picture those soft clouds floating in silence, light rippling through mist, colours blending, stars gently forming and fading. The night is patient, the cosmos is calm, and somewhere out there another nebula is beginning to breathe. If you'd like to keep wandering softly through the universe, you might enjoy other calm explorations here on The Sleepy Scientist. Perhaps the quiet rhythm of why light has a speed limit, the drifting stillness of Voyager beyond the stars, or the glowing pulse of the star that never sleeps. I'll put the links in the description, but for now, just rest. Let the colours fade and drift with them, into the calm, into the dark, and into dreams made of starlight.